Imagine for a moment that the universe we know, the vast, glittering expanse of stars, galaxies, and cosmic phenomena, is but a tiny fragment of a far greater reality, one stretching beyond the limits of our perception and understanding. The observable universe spans approximately 38 billion light years, teeming with countless galaxies, stars, and other cosmic wonders. Yet despite its seemingly endless expanse, the true boundaries of the universe remain shrouded in mystery. As we continue to push the boundaries of exploration, we are left wondering, what lies beyond the reach of our instruments? Is there a cosmic boundary where the very laws of physics as we understand them cease to apply, or could there be entirely different dimensions, realms waiting to be discovered, that exist just beyond our grasp? These questions fuel our curiosity, beckoning us to venture further into the cosmos. The observable universe is an immense arena encompassing everything we can see or detect, and it's bound by the speed of light and the age of the cosmos itself. The universe is believed to be approximately 8 billion years old, and within that time, light has traveled vast distances, carrying with it the information we need to understand the universe's structure and history. Think of light as a messenger sent from distant stars and galaxies, revealing their existence to us over unimaginable distances. However, we are only able to observe light that has had the time to reach us since the Big Bang. The universe itself is expanding, and as it stretches outward, it creates an ever-shifting boundary, marking the edge of the observable universe. Beyond this boundary lies the unobservable universe, a vast, hidden region that could house galaxies, stars, and phenomena that we are unable to detect with our current technology. These cosmic entities remain elusive, concealed from our view, and are part of a greater reality that remains largely unknown. To determine the bounds of this observable universe, scientists use a variety of tools and technologies. Telescopes, both on Earth and in space, capture the light emitted by distant celestial objects, allowing researchers to study the composition, movement, and distance of these objects. The redshift phenomenon, where light stretches to longer wavelengths as the universe expands, provides astronomers with a way to measure the distance between us and distant galaxies, revealing the very structure of the cosmos. The observable universe itself is estimated to span a colossal 90 to 100 billion light years in diameter. Within this expanse lies a staggering array of galaxies, stars, and cosmic phenomena, each piece contributing to our understanding of the universe's origins, its evolution, and its ultimate fate. Exploring this enormous framework provides not only a glimpse into the makeup of the cosmos, but also a window into the fundamental laws of nature that govern it. Modern telescopes, acting as our eyes to the universe, are indispensable tools for unraveling the mysteries of the cosmos. Optical telescopes gather visible light from distant stars and galaxies, allowing us to observe these celestial bodies in incredible detail. Meanwhile, radio telescopes capture radio waves emitted by distant phenomena, providing insight into parts of the universe that are otherwise invisible to the naked eye. One of the most significant breakthroughs in modern astronomy has been the development of space telescopes like the Hubble Space Telescope. Positioned beyond Earth's atmosphere, these instruments are free from the distortion caused by atmospheric interference, enabling them to capture clearer, more detailed images of distant cosmic objects. Hubble has been instrumental in providing breathtaking photographs and invaluable data about galaxies billions of light years away, giving us a glimpse into the universe's earliest stages and the processes that shape the stars and planets we observe today. Further enhancing our understanding of the universe are advanced technologies such as spectroscopy. This technique analyzes the light emitted or absorbed by celestial objects, breaking it down into its constituent wavelengths. By studying these spectra, scientists can determine crucial information about the composition, temperature, density, and even the motion of distant stars and galaxies. Spectroscopy offers a detailed picture of the life cycles of these celestial bodies, helping astronomers understand their formation, evolution, and the impact they have on the larger universe. In addition to telescopes and spectroscopy, the continued advancements in computing and imaging technologies play a critical role in our exploration of the cosmos. Modern computer algorithms are capable of processing vast amounts of data, uncovering hidden patterns, and providing insights that would be impossible to detect by the human eye alone. With these powerful tools, we inch ever closer to the edge of the observable universe, revealing the hidden mysteries that lay beyond the reach of our current understanding. Every new discovery, every breakthrough, invites even more questions and ignites a renewed sense of curiosity. As we look deeper into the vastness of space, we are constantly reminded of how much there is left to learn. Each step forward is a testament to human ingenuity and our relentless desire to uncover the unknown. At the heart of this cosmic exploration is the speed of light, a fundamental constant that governs much of what we know about the universe. Light travels at an astonishing 300,000 kilometers per second, and this incredible speed dictates how far we can see into the cosmos. The universe is approximately 14 billion years old, and light has had that long to travel to us from distant stars and galaxies. This distance determines the limits of our observational power, creating a vast yet inherently limited view of space. When we observe stars, galaxies, or any other celestial object, we are not seeing them as they are right now. Instead, we are seeing them as they were when the light first left them, sometimes millions or even billions of years ago. For example, when we observe a galaxy that is 7 billion light years away, we are witnessing it as it appeared 7 billion years ago. This phenomenon is known as look-back time, and it reveals a fascinating connection between our observations and the deep history of the universe itself. The farther away an object is, the longer its light has taken to reach us, allowing us to peer back in time. In a sense, every observation is a journey through the past, offering us clues about how the universe evolved and what it might become in the future. This concept of look-back time opens a window into the distant past, giving us a rare and invaluable glimpse into the cosmos as it once was. The universe is a vast and ever-expanding entity, filled with mysteries that continue to captivate our imaginations. Yet despite our growing understanding, it remains a boundless frontier, with much still hidden from our view. The more we discover, the more we realize how much is still left to explore. As we continue to develop new technologies and refine our understanding of the universe's fundamental principles, we are poised to uncover even more of the secrets that lie in the depths of space, secrets that have remained hidden for eons, waiting to be revealed. As the universe unfolds before us, one of its most striking features is the finite speed at which light travels, introducing an invisible boundary known as the cosmic horizon. Beyond this horizon, the flow of information is cut off, and no matter how advanced our technology becomes, we will forever remain unable to peer past this boundary. This isn't just a limitation imposed by our tools or instruments, it is rooted in the very nature of space and time itself. As the universe continues to expand, the reach of light grows increasingly constrained. Some regions of the universe are receding from us so swiftly that their light will never reach our eyes. These distant galaxies, though they exist, will remain forever hidden, shrouded in an impenetrable cosmic darkness. The implications of the speed of light in shaping our understanding of the universe are profound. It forces us to confront the fact that the observable universe is not static, it is dynamic, ever-changing. The limits of what we can observe are continuously shifting as the universe expands, creating a cosmos that is, in many ways, beyond our grasp. Light, in this context, serves a dual role. It acts as a bridge to our past, allowing us to peer into the early moments of the universe, while simultaneously being a barrier, preventing us from knowing what lies beyond our observational reach. This paradox invites us to reflect on the mysteries that lie just beyond our grasp, challenging us to wonder what secrets the universe holds outside the limits of our vision. One of the most intriguing and foundational theories in cosmology is that of cosmic inflation, which describes a period of incredibly rapid expansion in the very early universe. This phase, which is believed to have occurred just moments after the Big Bang, saw the universe expand at an exponential rate. Within an unimaginably short period, it grew from subatomic scales to roughly the size of a grapefruit. This brief but intense burst of expansion addresses several of the universe's most perplexing features, such as the uniformity of the cosmic microwave background radiation and the large-scale flatness of the universe. The connection between cosmic inflation and the size of the observable universe is profound. During the inflationary phase, regions of space that were once small became vastly separated. As a result, the observable universe we see today includes regions that were once in close proximity but became isolated due to the rapid expansion. This means that the universe's current size, estimated at about 93 billion light-years in diameter, has its roots in this initial inflationary period. The rapid expansion set the stage for the formation of galaxies, stars, and the large-scale structures we observe today. The tiny quantum fluctuations in density that existed during inflation were stretched across the cosmos, and over time, these fluctuations grew into the galaxies, clusters, and cosmic filaments that form the intricate web of the universe. Cosmic inflation not only provides a compelling explanation for the vastness of what we can observe, but it also helps to explain the intricate organization of the universe. The theory continues to gain support from a variety of observations, such as the detailed measurements of the cosmic microwave background and the distribution of galaxies. Each new discovery enriches our understanding of the early universe and deepens our curiosity about the mysteries that remain beyond the furthest reaches of our sight. In tandem with these revelations, the phenomenon of redshifts plays a crucial role in our understanding of the universe and its expansion. When we observe distant galaxies, their light appears stretched towards the red end of the spectrum. This shift occurs because these galaxies are moving away from us, and as they recede, the wavelengths of their light become longer. This effect, known as redshift, is akin to the Doppler effect we experience with sound waves. The pitch of a passing siren changes as it moves away from us. The concept of redshift was first explored by astronomer Edwin Hubble in the early 20th century. Through careful observation and measurement of the redshift in the light from various galaxies, Hubble discovered that the farther a galaxy is from us, the faster it appears to be receding. This groundbreaking discovery led to the revolutionary realization that the universe is expanding. Rather than being a static, unchanging entity, the cosmos is continuously stretching, a process that began with the Big Bang. The study of redshifts has since revealed even deeper layers of insight into the nature of the universe. The degree of redshift not only indicates how fast a galaxy is moving away, but it also provides valuable information about the history of the universe and the rate at which it has been expanding over time. This relationship led to the development of the Hubble constant, a key value that quantifies how the expansion rate changes with distance. As observational technology improves, scientists are now able to use redshift measurements to probe even more profound questions. Among these is the nature of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. Thus, redshifts are not merely markers of motion. They are vital clues that allow us to unravel the complex and evolving story of the universe. Yet, even as we make sense of the observable universe, we are confronted by some of its most perplexing mysteries. Dark matter, which makes up about 27% of the universe, remains one of the greatest challenges in modern cosmology. Despite its gravitational influence on visible matter, dark matter does not emit, absorb, or reflect light, rendering it invisible to our current detection methods. Scientists can only infer its existence by observing its effects on the motion of galaxies and galaxy clusters. However, the true nature of dark matter remains elusive, and despite numerous theories, no conclusive evidence for its identity has been found. Equally enigmatic is dark energy, which accounts for roughly 73% of the universe's mass energy content. This mysterious force is thought to be responsible for the accelerated expansion of the universe, but it remains poorly understood. Discovered in the late 20th century, dark energy challenges our comprehension of the cosmos, raising questions about its origin and its role in the future evolution of the universe. Some theories suggest that dark energy is a constant energy density inherent to space itself, but what causes this energy to exist and what its implications are for the universe's long-term fate remains an open question. Alongside these cosmic conundrums, another mystery that continues to baffle scientists is the imbalance between matter and antimatter. According to the laws of physics, the Big Bang should have produced equal amounts of both. However, the observable universe is dominated by matter, with only trace amounts of antimatter. This discrepancy presents a profound puzzle for cosmologists and particle physicists who have proposed various theories to explain how matter came to dominate the cosmos. These theories suggest that, in the early universe, certain processes may have favored the production of matter over antimatter, but this remains speculative. Solving this puzzle may unlock fundamental truths about the nature of the universe and the laws that govern it. These are the questions and mysteries that shape our understanding of the universe, a vast, ever-evolving expanse that continues to defy our comprehension. Each discovery opens new doors, but with each answer, new questions arise, urging us to look deeper and further into the cosmos. As we push the boundaries of our knowledge, we continue to uncover a universe that is as vast as it is mysterious, a cosmos that beckons us to explore its deepest secrets, even as it holds some of its most profound truths just out of reach. The question of cosmic inflation is one of the most profound and puzzling in the field of cosmology. This rapid expansion of the universe just after the Big Bang offers a tantalizing explanation for some of the universe's most fundamental features, such as its uniformity and flatness. Yet, despite its promise, the precise mechanisms that fueled this inflation remain a mystery. A multitude of inflationary models exists, each offering distinct theories about the pathways and forces that might have driven this explosive expansion. While these models provide insights into the early universe's behavior, the true nature of inflation continues to evade a complete understanding. Investigating the origins of this process could reveal far-reaching consequences, not just for our comprehension of the universe's infancy, but also for the very laws that govern all matter and energy. Every unanswered question serves to highlight the limitations of current knowledge, fueling an ever-deepening curiosity. This curiosity propels humanity's relentless quest for answers, as we peer into the vast expanse of the cosmos, striving to unlock its deepest secrets. Central to this exploration is the cosmic microwave background radiation, or CMBR, which acts as a crucial piece of the puzzle in understanding the universe's origins and its observable boundaries. The CMBR is a faint glow that permeates the entire universe, a relic from the very moment when the cosmos was still in its infancy. This afterglow, still detectable today, marks the moment when the universe had cooled sufficiently, around 370,000 years after the Big Bang, for protons and electrons to combine into hydrogen atoms, allowing light to travel freely. The radiation we observe today is the signature of this moment in time, providing a snapshot of the universe in its early stages. The CMBR not only illuminates the universe's beginnings, but also defines the limits of what we can observe. Due to the finite speed of light, we can only see light that has had enough time to reach us since the Big Bang. This means that the radiation we detect today comes from the furthest reaches of the universe, roughly 13.8 billion light-years away. Beyond this threshold lies a vast, invisible expanse, fundamentally inaccessible to us, no matter how advanced our technology becomes. As we study the CMBR, scientists have unlocked valuable clues about the universe's density, composition, and expansion rate. Variations in temperature, known as anisotropies, provide a map of the universe's earliest structures, revealing how tiny fluctuations evolved into the galaxies and clusters that fill the cosmos today. These fluctuations hold clues about the gravitational forces that have shaped the universe's growth, guiding cosmologists as they attempt to decode the forces at play. Moreover, the CMBR is not just a historical record, it also sets tangible limits on our understanding of the universe. The light we detect today reflects the state of the cosmos from when it was still young, but it also tells us that there is a vast portion of the universe that is forever beyond our reach. This boundary underscores the fact that no matter how far we progress in our explorations, there will always be regions of the cosmos that remain hidden from us. The study of the CMBR not only expands our knowledge of the universe's birth, but also provides insight into its possible fate. By analyzing the data collected from these ancient signals, cosmologists can test various theories about the forces driving cosmic expansion and try to predict how the universe might evolve in the distant future. These insights remind us of the vastness of the cosmos and the mysteries that remain unresolved, yet also offer a glimpse into its potential future. One such theory about the universe's ultimate destiny is the Big Freeze, or heat death. This scenario paints a chilling picture, rooted in the idea that the universe will continue to expand indefinitely. As it does, the energy within it will spread out across an ever-increasing volume of space. Over vast stretches of time, this expansion will lead to a gradual cooling of the universe. Stars will burn out, galaxies will drift farther apart, and all matter will eventually be left in a state that approaches absolute zero. The cosmos will become increasingly empty, dark, and cold, and the stars that once illuminated the night sky will fade away, transforming into white dwarfs, neutron stars, or even black holes. These stellar remnants, however, will not last forever. Over the course of trillions of years, they will slowly decay, radiating energy and eventually evaporating in a process known as Hawking radiation. Eventually, even black holes will disappear, leaving behind a cold, dark void filled with nothing but elementary particles. In this scenario, the universe will be a place devoid of usable energy, and all physical processes will grind to a halt. This period of ultimate stillness, where entropy reaches its peak, is known as the heat death of the universe. During this phase, there will be no room for life as we know it, and the cosmos will be eerily silent. The Big Freeze offers a haunting, scientifically grounded vision of the universe's end, where everything fades into a quiet, frozen eternity. In stark contrast to this notion of an ever-expanding universe, the Big Crunch presents a more explosive theory about the universe's fate. According to this theory, the universe, currently expanding, could eventually slow down and reverse its course, collapsing in on itself. This contraction would lead to the universe's ultimate demise, as all matter and energy are drawn back into a single, incredibly dense point. The Big Crunch represents an end that is both catastrophic and final, offering a more dramatic and fiery vision of the universe's conclusion, one that contrasts sharply with the Big Freeze's cold, quiet solitude. Both theories, though vastly different in their predictions, offer a glimpse into the universe's uncertain future. They highlight the unpredictable nature of cosmic evolution, showing that while we may have a solid understanding of the universe's past, its future remains as mysterious as its origins. As we continue to unravel these cosmic enigmas, we move ever closer to understanding not only where we came from, but also where we may be headed. This theory proposes a fascinating vision for the universe's future, suggesting that after a prolonged period of expansion, the universe could eventually reverse direction and begin contracting. As galaxies are drawn closer together, the density of matter would increase dramatically, reshaping the cosmic landscape in ways we can barely imagine. The gravitational force, acting as the universe's ultimate pull, would be the driving force behind this contraction, drawing everything from stars and galaxies to dark matter itself back toward a singularity. Visualize this process as a vast cosmic balloon, its air gradually being let out, causing the surface to shrink. As it deflates, the distant stars, once separated by unimaginable distances, would gradually converge. This grand reversal could culminate in what is known as the Big Crunch, a moment when the entire universe collapses into an infinitesimally small point of infinite density, a singularity where the very laws of physics as we understand them cease to apply. Such a scenario raises profound questions about the nature of space, time, and the limits of our knowledge. If the universe were to collapse into a singularity, could the collapse trigger a new cycle of expansion? Perhaps our universe could undergo an endless series of births, lives, and deaths, each iteration playing out in a cosmic cycle. This idea fuels much of the debate among cosmologists about the true nature of the universe's long-term behavior and the fundamental essence of time itself. While observations of the universe today suggest an accelerating expansion driven by the mysterious force known as dark energy, the Big Crunch remains a compelling theoretical possibility, sparking our imagination about the cosmos's future. It serves as a reminder that the universe is dynamic and ever-changing, its fate uncertain and yet brimming with infinite possibilities. Meanwhile, another theory, the Big Rip, offers a strikingly different fate for the cosmos. This scenario imagines that the universe's current accelerated expansion, driven by dark energy, could eventually lead to the catastrophic tearing apart of all matter. In this future, the force behind dark energy would grow stronger and stronger over time, causing everything from galaxies to atoms to be ripped asunder. The ultimate result would be a universe devoid of structure, a vast expanse of isolated energy streaks with no galaxies, no stars, no planets, and no recognizable matter. Evidence supporting the Big Rip primarily comes from the observation of distant supernovae. These explosions appear dimmer than expected, which suggests that the universe's expansion rate has been accelerating over time. Additionally, the study of the cosmic microwave background radiation, the afterglow of the Big Bang, provides further insights into the structure of the universe and its expansion. Certain models of dark energy predict that if its density increases over time, the Big Rip could be our ultimate end. However, the Big Rip is far from the only scenario that could play out. Other competing theories, like the Big Freeze and Big Crunch, offer alternative outcomes for the universe's future. The Big Freeze suggests that as the universe continues to expand, it will cool over billions of years to the point where all stars will burn out, leaving a cold, dark, and lifeless expanse. In stark contrast, the Big Crunch posits that gravitational forces could eventually reverse the expansion, drawing everything into a singularity. While the Big Rip suggests a violent and sudden end, current observations of dark energies suggest that its influence may remain constant over time, leading to a more gradual, slow expansion. This possibility would rule out the explosive tearing apart of the universe as predicted by the Big Rip. Despite these differing theories, the Big Rip still presents a dramatic and compelling thesis about the end of everything. Ongoing research into dark energy continues to evolve our understanding of the cosmos, keeping the door open to various potential outcomes. It serves as a reminder that the universe, in all its majesty, is an ever-changing, evolving entity. The concept of the multiverse, however, shakes the very foundation of our understanding of the cosmos. Traditionally, we have viewed our universe as a singular, bounded entity, existing within its own defined edge. But the multiverse theory proposes that our universe is just one of many, potentially infinite universes, each existing simultaneously. This theory challenges the notion of a singular boundary, suggesting that what we perceive as the universe is merely a small piece of a far grander cosmic structure. In the multiverse model, different universes might have entirely different physical laws, constants, and even dimensions. Some could be nearly identical to our own, while others may be wildly different in ways we cannot yet fathom. The idea of a multiverse fundamentally changes the concept of cosmic boundaries. Instead of one universe with a clear edge, there could be an infinite array of universes, each with its own unique properties and laws, expanding our understanding of the very notion of space. This perspective raises profound questions about the origin and nature of our universe. If there are multiple universes, the events that led to the formation of our own may be only a small part of a much larger and more complex cosmic history. The theory of cosmic inflation, which suggests that the universe underwent a rapid expansion just after the Big Bang, gains new depth in this multiverse framework. In this view, inflation may not have been confined to a single universe, but could be happening in countless other bubble universes, each one expanding in its own way, giving birth to diverse cosmic realities. Ultimately, the multiverse theory invites us to reconsider our place in the cosmos. Rather than being the focal point of a single universe, we may occupy a tiny corner of an immensely larger, more intricate multiverse, a concept that could forever change how we understand reality and our role within it. This radical idea not only sparks the imagination of cosmologists, but also challenges humanity to dig deeper into the mysteries of existence and the fundamental nature of all things. The question of whether the universe is finite or infinite has long been a topic of intense debate within the field of cosmology. Proponents of an infinite universe argue that, based on the principles of geometry, the cosmos could extend endlessly in all directions without a definitive edge or boundary. Such a notion aligns with the theory that the universe is flat on a large scale, suggesting that the universe could stretch infinitely with no true beginning or end. If this is the case, it paints an image of a universe that will continue to grow and evolve endlessly, where stars may flicker across an ever-expanding vastness. On the other hand, those who support the idea of a finite universe point to the observable universe and its well-defined structure. They argue that the cosmic background radiation and the distribution of galaxies offer clues indicating that the universe has boundaries. Observations also suggest that the universe has a finite age, around 13.8 billion years since the Big Bang. This implies that if we could trace the universe's history backward, we might eventually encounter a point of origin, which could signify the finite nature of the cosmos. Another intriguing argument against the idea of a finite universe lies in the theory of cosmic inflation. This concept suggests that in the moments following the Big Bang, the universe underwent a rapid expansion, a process that would have brought distant regions into contact. This rapid inflation could have created a larger, more complex structure than we can observe today, potentially challenging the idea of a finite universe. In the end, whether the universe is infinite or finite remains one of the most captivating and unresolved questions in cosmology. The search for answers continues to drive research, providing new insights into the nature of space, time, and the very fabric of existence itself. However, the finite model proposes a thought-provoking idea. The expansion of the universe may one day come to a halt, especially if gravitational forces ultimately dominate. This would lead to a scenario where the universe collapses inward, potentially in a finite existence rather than an eternal one. When we delve into the conflicting viewpoints of these cosmological models, we see that they highlight the significant limitations of our current understanding. They also underscore humanity's relentless quest for answers about the fundamental nature of the universe. The question of whether the universe is infinite or finite is not only a matter of scientific curiosity, it's a profound challenge that continues to inspire researchers to dig deeper into the cosmos. As we gather more observational evidence and refine our theoretical models, the truth behind this cosmic question may one day be within our grasp. But for now, it remains one of the most profound and unresolved topics in modern science. String theory, a cutting-edge concept in theoretical physics, provides an intriguing lens through which we can explore the nature of the universe's boundaries. Unlike traditional particle physics, which treats particles as point-like objects, string theory proposes that the very fabric of reality is composed of tiny vibrating strands of energy, strings. This concept radically expands our understanding of the universe, suggesting that the dimensions we experience, 3 dimensions of space and 1 of time, might not be the only ones in existence. String theory hints at the possibility of additional dimensions, up to 10 or even 11, folded and compacted at scales smaller than we can currently observe. This revelation opens up fascinating possibilities about the structure of the universe, potentially eliminating the notion of a boundary in the conventional sense. Some models suggest that the universe could be infinitely large, with dimensions folded upon themselves in intricate patterns that our senses cannot detect. What we perceive as the edges of the universe might in fact be the limits of our observational tools, not the boundaries of space itself. Moreover, string theory aligns with cosmological ideas that seek to unravel the mysteries of the universe's origins. By integrating the principles of quantum physics and general relativity, string theory may offer a new framework for understanding the universe's birth. The moments immediately following the Big Bang remain some of the most enigmatic in cosmology, and string theory might provide the missing link. It suggests that quantum fluctuations in the early universe could have sparked the density waves that shaped the formation of cosmic structures like galaxies. In this way, string theory not only addresses the question of the universe's boundaries, but also poses intriguing new questions about the very fabric of space and time. What lies beyond our observable universe? How can we comprehend the vastness of space when our senses are confined to a limited slice of reality? Although string theory does not provide definitive answers to these profound questions, it contributes to the ongoing conversation about the universe's extent and its fundamental nature. By suggesting a multidimensional reality, it challenges the current understanding of boundaries, not as mere physical limits, but as part of a much deeper, more intricate cosmic tapestry. This broader perspective compels scientists to think beyond the confines of what we can observe, prompting further exploration into the hidden dimensions that may govern the universe's true structure. These unobservable dimensions could have a profound impact on the way we understand the universe we live in, encouraging a continual expansion of our intellectual horizons. The notion of higher dimensions extends far beyond our daily experience, yet it plays a crucial role in modern theories about the universe. Traditionally, we perceive the world through the lens of 3 spatial dimensions and 1 temporal dimension. Yet, physicists are exploring the possibility that more dimensions could exist, influencing not only the structure of the cosmos, but also the very behavior of the forces that govern it. The concept of higher dimensions offers potential solutions to some of the most unresolved questions in cosmology, especially regarding the nature of the universe's ultimate boundaries. In theories such as string theory, higher dimensions are not simply abstract mathematical ideas, they are considered fundamental elements of reality. String theory suggests that the universe's smallest constituents are not point-like particles, but rather tiny, vibrating strings. These strings exist in a space that may involve up to 10 or 11 dimensions, dimensions beyond the 4 we experience in our daily lives. Some of these extra dimensions may be compacted or curled up so tightly that they remain imperceptible to us at everyday scales. Yet, they could become evident in certain conditions, such as at quantum or cosmological scales. The allure of these higher dimensions lies in their potential to unify the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, into a single cohesive framework. This unification could offer a more complete understanding of the universe, revealing a seamless fabric that connects all particles and forces. In doing so, it challenges our perception of space and time, urging us to reconsider the very nature of reality itself. As we explore the concept of higher dimensions, we are drawn into a deeper curiosity about what lies beyond our immediate experience. What if the universe we perceive is just a small part of a much larger, multidimensional cosmos? This idea sparks endless questions and encourages scientists to push the boundaries of what we know, forever expanding the horizons of human knowledge. Moreover, the pursuit to comprehend the existence of higher dimensions pushes the boundaries of our imagination, challenging our very understanding of the cosmos. If such dimensions indeed exist, they could fundamentally reshape the limits of what we know, revealing a universe far more intricate, vast, and interconnected than we could ever have conceived. This ongoing exploration ignites the curiosity of scientists, urging them to delve deeper into the fabric of existence and explore the infinite possibilities that could be at play, shaping the very cosmos we inhabit. As researchers continue their journey into this uncharted territory, they bring us ever closer to unlocking the mysteries that lie just beyond our perceptual reach. The observable universe, a vast and awe-inspiring expanse, extends over 13 billion light-years in every direction. It encompasses everything we are currently able to detect or measure. However, beyond this horizon, the mystery only deepens. While scientific models suggest that the universe stretches far beyond what we can see, we lack direct evidence of what lies beyond our observational limits. Theories postulate that the universe may in fact be infinite, extending into realms beyond our comprehension, filled with countless galaxies, clusters, and possibly even entirely different laws of physics and constants that govern them. This opens up the possibility that although we can visualize a bubble of space surrounding us, there is an entire universe beyond it, teeming with stars and planets, some of which may remain forever out of our reach. One particularly captivating hypothesis suggests that the universe is not merely infinite, but rather exists as part of a multiverse. This concept proposes that our universe is just one of many, each operating according to its own unique set of physical laws. In this framework, some universes might feature entirely different structures, forces, or even realities, coexisting in a vast network of universes. The idea of a multiverse radically shifts our perspective, offering an entirely new way of understanding the cosmos and our place within it. Furthermore, regions of space that lie beyond the observable universe may be expanding faster than the speed of light due to cosmic inflation, a rapid expansion that occurred in the moments following the Big Bang. This theory suggests that many areas of space will remain inaccessible to us, forever beyond our reach. The faster-than-light expansion means that no matter how advanced our technologies become, these regions will remain shrouded in mystery, just out of our grasp. The ongoing quest to understand what lies beyond this boundary of observation not only challenges the very limits of science, but also fuels our imagination, inspiring a deeper exploration into the underlying nature of reality itself. The cosmic horizon, a boundary that marks the farthest we can see, represents the frontier of our observational abilities. Beyond this limit lies a realm that is still enshrouded in enigma. However, driven by an insatiable curiosity and the laws of physics, scientists have formulated several hypotheses regarding what might exist beyond this boundary. This limit is determined by two key factors: the age of the universe and the speed of light. Essentially, we can only observe objects whose light has had enough time to travel to us since the Big Bang, and therefore anything beyond this light's reach remains hidden from our eyes. One of the primary concepts utilized by scientists to probe the universe's depths is cosmic inflation. This theory proposes that in the first moments following the Big Bang, the universe underwent an exponential expansion, vastly increasing its size. If this theory holds, then beyond our observable universe, there could exist regions of space vastly different from our own. These regions might contain galaxies and cosmic structures that bear little resemblance to those within our cosmic horizon. This idea challenges the very essence of our understanding, suggesting that our observable universe is but a small piece of a far grander cosmic puzzle. Additionally, the notion that the universe could be infinite adds yet another layer of intrigue. If the universe is indeed infinite, then there could be an endless expanse of space filled with countless galaxies, stars, and possibly even life forms far beyond anything we can currently detect. This concept challenges our perception of the universe's structure, implying that the small slice we can observe is just a minuscule fragment of a vastly larger reality. Finally, some scientific hypotheses delve into the speculative realm of multiverse theory. This idea proposes that our universe is just one of many, each with its own set of physical laws and constants. Such a concept stretches the boundaries of our understanding and invites us to reconsider what we know about reality itself. Though these ideas remain speculative and theoretical, they highlight the extraordinary ingenuity of human inquiry, propelling us to seek answers to the cosmos's ultimate questions. This search for knowledge fosters a sense of wonder and awe, urging us to explore the vast unknown that extends far beyond our current observational limits. As we gaze into the infinite expanse of the cosmos, we are acutely aware of the constraints imposed by the observable universe. While the universe extends far beyond the reach of our telescopes and instruments, scientists utilize a variety of tools and methods to offer us fleeting glimpses into these otherwise inaccessible regions. One of the most promising approaches involves the study of cosmic background radiation, an ancient afterglow from the Big Bang that permeates the universe. This faint radiation holds valuable clues about the early stages of the universe and hints at what might lie beyond our ability to observe. Another powerful tool at the disposal of researchers is the detection of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. By studying these waves, scientists can infer events that occurred in regions far beyond our line of sight, such as black hole mergers or neutron star collisions. The detection of gravitational waves has revolutionized our understanding of these cataclysmic phenomena, paving the way for new insights into the structure and history of the universe. In sum, while the limits of our observation may constrain our understanding of the cosmos, the relentless curiosity of scientists continues to push the boundaries of what is known. Through creative theories, innovative tools, and a spirit of exploration, humanity edges ever closer to unraveling the profound mysteries that lie beyond the observable universe. The journey to understand the unknown may never truly end, but with each step forward, we come closer to comprehending the vast, interconnected reality that surrounds us. In the quest to explore the vast and enigmatic expanse of the cosmos, scientists rely on a myriad of methods that extend far beyond our direct visual perception of the universe. Through simulations, theoretical models, and advanced technology, they push the boundaries of what we know, unveiling the hidden forces and components that shape the universe's evolution. Simulations and theoretical models form the backbone of this exploration. Scientists develop intricate computer models that mimic the universe's evolution, applying the fundamental laws of physics to predict behaviors in regions that remain invisible to our current observational tools. These models provide invaluable insights into phenomena like dark matter and dark energy, the mysterious and largely unexplained elements that dominate the universe. While these components remain poorly understood, they exert a profound influence on the universe's structure and expansion, guiding researchers in their quest to unlock the secrets of the cosmos. Advancements in technology, particularly in the realms of radio and infrared astronomy, have enabled scientists to peer through the obscuring layers of cosmic dust and gas. This allows for the observation of objects that would otherwise remain hidden from conventional optical telescopes. By utilizing different wavelengths of light, astronomers can gather critical data about galaxies, stars, and planetary systems that lie beyond our direct line of sight. These technological strides ensure that our understanding of the universe is not limited to what is immediately visible, offering a more comprehensive view of the cosmos and revealing objects and phenomena that would otherwise remain inaccessible. In recent years, the study of gravitational waves has transformed our understanding of the universe, providing an entirely new perspective on its most violent and distant events. Gravitational waves are ripples in the fabric of space-time, created by some of the most catastrophic events in the universe, such as the collision of neutron stars or black holes. These disturbances, though faint, travel through space and can be detected on Earth by instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. By analyzing the frequency, amplitude, and patterns of these waves, scientists can extract valuable information about the events that generated them. The mass of the colliding objects, the distance from Earth, and even the dynamics of the event itself can be inferred from the signals they produce. What makes gravitational waves particularly remarkable is their ability to pass through matter largely unimpeded, unlike light, which can be blocked or altered by cosmic dust and gas. This property allows them to reveal hidden regions of space that would otherwise be obscured from view. Gravitational waves offer an unparalleled opportunity to study phenomena that would be invisible to traditional electromagnetic observations, such as those made by telescopes. As more gravitational wave events are detected and analyzed, astronomers are poised to uncover new and profound insights into the fundamental nature of the universe, shedding light on the nature of dark matter, dark energy, and the evolution of the cosmos itself. At the same time, researchers are expanding our understanding of the universe's size and scale. The observable universe, which extends about 13.8 billion light-years from Earth, represents the portion of the cosmos we can study directly. However, it is widely believed that the universe stretches far beyond this limit and could be infinitely large. This realization has sparked a quest to understand the true extent of the universe, with key insights coming from the observation of distant galaxies. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery. Galaxies are moving away from us. By measuring how fast galaxies recede from Earth, scientists can estimate their distances and, by extension, calculate the rate at which the universe is expanding. This rate, known as the Hubble constant, provides critical information about the overall growth of the universe. The expansion of the cosmos is ongoing, pushing regions of space further out of our observational reach and suggesting that the universe is far larger than we can currently perceive. One of the key tools for understanding the early universe is the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation, which is nearly uniform across the sky, offers a snapshot of the universe's state just a few 100,000 years after the Big Bang. By studying small fluctuations in this radiation, scientists can glean information about the universe's composition, geometry, and overall structure. These fluctuations serve as a cosmic fingerprint, helping researchers estimate the mass and density of the universe, thereby providing clues to its shape and extent. Theoretical models and simulations also play a pivotal role in estimating the universe's overall size and evolution. By incorporating the effects of dark energy and dark matter into these models, astrophysicists can predict how the universe might evolve over time. These simulations suggest that the universe could be vastly larger than what we can observe, potentially stretching infinitely in all directions. This realization challenges our understanding of space itself and fuels ongoing research into the universe's true boundaries. Dark matter and dark energy represent two of the most profound mysteries of modern astrophysics. Although only about 4% of the universe is made up of ordinary visible matter, the remainder is dominated by these invisible forces. Dark matter, which accounts for approximately 26% of the universe's mass, does not emit, absorb, or reflect light, making it impossible to detect through conventional methods. Despite its elusiveness, dark matter's presence is inferred from its gravitational effects on galaxies and galaxy clusters. Without dark matter, the universe's structure would not be as it is. Galaxies would not hold together, and cosmic forces would not behave as observed. In addition to dark matter, the universe is also influenced by dark energy, which is believed to make up roughly 70% of the universe's energy content. Dark energy is thought to be responsible for the accelerated expansion of the universe. Its nature remains one of the most significant unsolved problems in modern science, and understanding it is crucial for comprehending the fate of the universe. The journey to unravel the mysteries of dark matter and dark energy is an ongoing one. Each discovery, each simulation, and each technological breakthrough brings scientists closer to understanding the true nature of the cosmos. As our tools and techniques continue to evolve, we are granted new insights into the vast, intricate, and awe-inspiring universe that surrounds us. Through these groundbreaking methods, we are not merely exploring what is visible to us, but expanding our reach into the unknown, inching ever closer to answering some of the most profound questions in science. However, its presence is inferred not by direct detection, but through the gravitational effects it has on visible matter. For example, galaxies rotate at such high speeds that, based on the amount of visible mass alone, they should simply tear themselves apart. Yet they remain intact, suggesting something unseen is at play. Dark matter is the mysterious substance that provides the gravitational glue holding galaxies together. This discovery has revealed a humbling truth. What we can observe with our instruments and eyes is just a fraction, a mere tip of the cosmic iceberg, in a universe that holds far more than meets the eye. In stark contrast, dark energy, an even more elusive phenomenon, makes up about 70% of the universe. It is responsible for the accelerating expansion of the cosmos. While gravity pulls matter together, dark energy works in the opposite direction. On the largest scales, it pushes galaxies apart, causing the universe to stretch ever more rapidly. As astronomers delve deeper into the cosmos, they realize that understanding how dark matter and dark energy interact may unlock profound insights into the ultimate fate of the universe. Could galaxies drift endlessly apart in an ever-expanding void? Or, conversely, might the influence of dark energy lead to a dramatic cosmic collapse, where vast networks of galaxies form a sprawling web? The more we investigate these unseen forces, the more it becomes clear that our current observations might only scratch the surface of what the universe truly is. These mysteries prompt us to ask questions that lie far beyond the capabilities of current technology to answer. The dynamics of dark matter and dark energy not only reshape the structure of the universe, but also invite deep speculation about the cosmos's future trajectory. As research progresses, the pursuit of understanding these cosmic enigmas remains central to unlocking the universe's most profound secrets. Our exploration touches on a vast expanse that far exceeds the boundaries of what we can observe. Quantum mechanics and cosmology, those seemingly disparate realms of science, converge in fascinating and often perplexing ways when probing the deepest unknowns of the universe's edge. At its core, quantum mechanics governs the behavior of the smallest particles in the universe, particles like electrons and photons, which make up the building blocks of everything. Cosmology, on the other hand, is concerned with the grand-scale phenomena that shape the universe: galaxies, stars, black holes, and the fabric of space-time itself. However, where these two fields meet is where the true magic of the cosmos resides. The laws that govern the smallest elements of matter can profoundly affect the larger structures of the universe, often in ways that are difficult for us to comprehend. One of the most intriguing examples of this intersection occurs during the universe's infancy, shortly after the Big Bang. During this time, quantum fluctuations, minute variations in the energy of empty space, played a pivotal role in shaping the distribution of matter throughout the universe. These fluctuations, rooted in the quantum realm, were amplified during a process called cosmic inflation, a period when the universe expanded at an astonishing rate in the blink of an eye. It was in these fractions of a second that the initial seeds for galaxies, stars, and all cosmic structures were sown. Moreover, black holes stand as another fascinating intersection between quantum mechanics and cosmology. These enigmatic objects possess such immense gravitational pull that not even light can escape. The study of black holes challenges our understanding of both gravity and quantum physics. Theoretical physicists speculate that at the very edge of a black hole, where gravity is so intense that it warps space-time itself, quantum effects take over, dictating how particles and information behave. Some theorists believe that a unified theory of quantum gravity could offer the answers to these questions, unveiling not only the secrets of black holes, but perhaps even the true nature of the universe's edge. The quest to understand dark energy and dark matter, together comprising about 95% of the universe, is also deeply embedded in the realms where quantum mechanics and cosmology overlap. The quantum properties of these hidden cosmic components could provide crucial insights into the universe's expansion. As we continue to explore and merge these fields, we stand on the precipice of breakthroughs that might completely transform our understanding of the universe and its hidden boundaries. Throughout history, humans have envisioned the edge of the universe in diverse and imaginative ways, each culture contributing its own unique perspective. In ancient Mesopotamia, for example, the universe was often imagined as a vast, flat expanse covered by a dome-shaped sky. This celestial dome was believed to shelter the heavens and the gods, while the earth lay beneath, at the center of this cosmic architecture. For these ancient peoples, the edge of existence was marked by a boundary that separated the physical world from the divine, a limit that hinted at an unseen, otherworldly realm. In contrast, the ancient Greeks offered a different cosmological model. Philosophers like Pythagoras, Plato, and Aristotle conceptualized the universe as a series of concentric spheres, with the Earth at the center. For them, the universe had a definitive edge, with the fixed stars residing on the outermost celestial sphere. This belief evolved over time, particularly during the Renaissance, when astronomers like Copernicus and Galileo challenged the Earth-centered view of the cosmos. The shift from a geocentric to a heliocentric model redefined the edge of the universe, suggesting that the cosmos was not a finite, bounded system, but something far more expansive. Eastern philosophies, too, offer intriguing perspectives on the universe's limits. In Hindu cosmology, the universe is understood as cyclical, constantly undergoing phases of creation and destruction. Here, the idea of an edge is not about a physical boundary, but about the continuous flow of time and the eternal cycle of existence. Similarly, in Chinese cosmology, the concepts of yin and yang highlight the interconnectedness and balance of all things. For this worldview, the universe does not have a definitive boundary. Instead, it flows in an endless, harmonious cycle, with no fixed beginning or end. Today, scientific views have shifted to a more sophisticated understanding of the universe, recognizing its boundless expansion and the ever-increasing complexity of cosmic structures. Yet, despite these advancements, the rich cultural and philosophical depictions of the universe's edge continue to resonate with us. These ideas, passed down through generations, remind us that our quest to understand what lies beyond the observable universe is not merely a scientific endeavor, but a profound human journey, a search that transcends reason and stretches deep into the realm of imagination and wonder. The nature of the universe, whether finite or infinite, raises profound existential questions. If the universe is infinite, it suggests a reality without limits, an endless expanse where the possibilities for life, events, and even the laws of physics may stretch without end. In such a universe, some might find comfort in the idea that anything is possible, that every conceivable reality exists somewhere within this boundless cosmos. The notion that our individual lives, though fleeting, are part of this vast, infinite tapestry offers both a sense of humility and significance. In this infinite reality, every possibility is realized, and perhaps even the improbable becomes the inevitable. The universe, in its boundless expanse, becomes a canvas upon which every conceivable event, every possible form of existence, plays out in a grand cosmic symphony. The question then becomes, what is our place in this vast, infinite cosmos? What does it mean to exist in a universe without boundaries? As we continue to explore and expand our understanding, the answers to these questions remain ever elusive, but they fuel our curiosity and deepen our sense of wonder at the extraordinary mysteries that lie before us. Conversely, if the universe is finite, it introduces a profound and distinct set of implications, both physical and philosophical. A finite universe suggests that there are boundaries to our existence, not only in terms of the physical space we occupy, but also perhaps in time itself. This realization raises significant questions about the nature of our reality. What is the scope of the universe, and what does it mean for our role within it? The very idea that there might be a point beyond which there is nothing, that the cosmos has limits, brings forth an underlying urgency to understand our surroundings more deeply and grasp our place in the grand cosmic narrative. The concept of a finite universe stirs a contemplation of mortality, not only of human life, but of the universe itself. Does the universe have a definitive beginning, a moment where it came into being? Will it at some point come to an end? These are questions that blur the lines between science and philosophy, prompting us to explore our existential legacy. If the universe is finite, it might compel us to seek meaning in the fleeting moments of our existence, highlighting the brevity of life against the backdrop of an immense and possibly impermanent cosmos. In this context, the limitations of time and space may become a catalyst for us to find deeper purpose in the short duration of our lives. Both infinite and finite views of the universe force us to confront the notion of our mortality and the very nature of consciousness. In an infinite universe, the awareness of countless possible realities can make us question the significance of individual human experience. Do the infinite possibilities of existence diminish our sense of purpose, or do they elevate our understanding of interconnectedness? On the other hand, in a finite universe, the recognition of limits might encourage us to cherish each moment more deeply, to seek purpose within our brief span of existence. In either case, these cosmic reflections serve as a mirror, reflecting our deepest hopes, fears, and aspirations. Whether the universe is boundless or finite, it calls us to question not only the stars above, but also the essence of our being and our search for knowledge, meaning, and connection. The very notion of the universe's edge, its boundaries, carries profound implications that transcend cosmology and touch upon the very core of human existence. Current scientific theories suggest that the universe is constantly expanding, but this leads to questions that extend beyond the physical. What lies beyond the observable limits of space? Is there something further, something beyond what our instruments can detect or comprehend? This ever-expanding view of the universe invites us to consider not only the physical universe, but also our place within it, in ways that challenge traditional paradigms of existence. Philosophically, the idea of an edge pushes us to reconsider the meaning of existence itself. If the universe has boundaries that we cannot see or fully understand, what does that imply for our place in this vast expanse of creation? Are we insignificant specks in an infinite, boundless cosmos, or is there an intrinsic value to our existence as conscious beings capable of contemplating the very nature of the universe? The idea of an edge to the universe evokes awe, inviting deep reflections on purpose, existence, and our connection to something much greater than ourselves. Theories about the universe's edge also invite a view of cosmology as an ever-evolving discipline. As scientists continue to make discoveries and push the limits of our understanding, they unveil new dimensions of our cosmos, which in turn provoke new philosophical questions. This dynamic relationship between science and philosophy has the potential to break down rigid boundaries, encouraging a more integrated and holistic approach to understanding life, existence, and the universe. The more we learn about the cosmos, the more we realize how much remains unknown, fueling an ongoing journey of inquiry and discovery. Ultimately, the question of the universe's boundaries serves as a mirror, reflecting not only our search for knowledge, but also our deeper innate desire to understand who we are in this vast, ever-expanding reality. The search for answers intertwines with the search for meaning, and in this quest, we find ourselves as humans part of a shared narrative of curiosity. We are all explorers, not just of the stars above us, but also of the depths of existence itself, constantly seeking to understand our origins, our purpose, and our place in the grand scheme of the universe. The search for the edge of the universe, whether in terms of its physical limits or its existential implications, resonates with the age-old philosophical quests for meaning. Both endeavors ask us to confront questions that may never have definitive answers. As astronomers extend their instruments, peering into the depths of space, they are not merely investigating the boundaries of the physical universe. They are also probing the edges of human existence, seeking to unravel the mysteries of our origin, our destiny, and our role in this vast, evolving cosmos. This pursuit of knowledge through both science and philosophy reveals a deep, shared drive to understand the world and our place within it. The methods may differ. Science relies on observation, experimentation, and abstract theory, while philosophy depends on critical thinking, reasoning, and dialogue, but the motivation is the same, an unrelenting desire to connect with something greater than ourselves. Whether we are pondering the nature of the multiverse in quantum physics or questioning the nature of good and evil in ethics, both scientists and philosophers share a common goal: to bring clarity to the mysteries that shape our understanding of existence. In both fields, perspective plays a crucial role. Just as a philosophical shift can transform our understanding of morality or existence, so too can a shift in our cosmic perspective alter how we see ourselves in the vastness of space. When we contemplate the unimaginable scales of the universe, its incomprehensible distances, and the billions of years that stretch behind us, we may feel insignificant, small, against such enormity. Yet, at the same time, this vastness can make us acutely aware of our integral role in the story of existence. Therefore, the exploration of the universe and the philosophical search for meaning are not separate pursuits, but are deeply interconnected. Both serve to enrich our understanding of ourselves, our origins, and our ultimate purpose. As we search for the edges of the universe, we also search for the edges of our own understanding, unraveling the mysteries that define our existence in the grand tapestry of the cosmos. As we move forward, both in our exploration of space and in our philosophical inquiry, we continue to push the boundaries of knowledge, always questioning, always seeking. However, the very notion of an edge forces us to confront profound questions about what lies beyond it, and how such an understanding might reshape our perception of the universe. At the heart of this inquiry lies the very essence of space itself. In a finite universe, one might imagine a boundary akin to the surface of a balloon. As the balloon expands, every point on its surface moves farther away from each other. Yet crucially, there is no actual edge in the traditional sense within three-dimensional space. This analogy offers a glimpse into how space could be structured. Rather than containing a hard, discernible boundary, the universe might instead be curved. This curvature could make it possible to travel in a straight line and, after an infinite distance, return to your original starting point, much like navigating the surface of a sphere. This concept challenges the conventional view of space as a static, unchanging backdrop, suggesting instead that it is a dynamic continuum, forever evolving. Such ideas compel us to rethink the very nature of existence. If the universe itself could be curved, if it could be infinite, then perhaps the limits of our physical reality are not so straightforward. Time, too, must be considered in this context, as it often runs parallel to our understanding of space. If the universe possesses an edge, then the very fabric of time itself could have a beginning or an end. Current theories, including the widely accepted Big Bang model, imply that time itself originated with the universe, suggesting that before this moment there was no before at all, a concept that is nearly impossible for us to fully grasp. The intricate relationship between space and time leads to even more complex questions. Could time be cyclical rather than linear? Is it possible that time, like space, could loop back on itself, creating alternate realities or even multiple timelines? These theories encourage us to reconsider our traditional linear understanding of time and open the door to more fluid and multidimensional models of existence. Ultimately, grappling with the idea of the universe's edge pushes us to confront the limitations of our understanding, challenging us to venture deeper into the unknown. It forces us to embrace the possibility that time and space may not operate in the rigid, predictable ways we have long assumed. Whether we are contemplating the concept of a cosmic boundary or the infinite expanse that might lie beyond it, each inquiry invites us to expand our vision of the universe, making us appreciate its profound complexity and our seemingly small place within it. As we seek to comprehend the vastness of space and the future of the universe, we are inevitably drawn into considerations that touch upon the ethical dimensions of existence. Theories about the universe's ultimate fate, whether it is the heat death of the cosmos, a big crunch, or a potential rebirth through cosmic inflation, can have far-reaching implications for how we live today. When we consider the final end of everything, our own mortality included, it often evokes a profound sense of our own insignificance in the grand, seemingly infinite scope of the cosmos. And yet, this awareness can also spark a sense of urgency. Realizing how small our moment in time truly is may inspire us to value the experiences we have, to cherish each moment, and to prioritize deep and meaningful connections with others. For many, the inevitable passage of time and the certainty of eventual endings encourage a hedonistic or experiential approach to life. If time is limited, they argue, then perhaps the best course of action is to savor pleasure, to invest in personal relationships, and to focus on fulfilling, joyful experiences. This mindset reflects philosophies that advocate for living fully in the present moment, emphasizing mindfulness and the importance of being here, now. These ideals echo the teachings of various traditions, from ancient Stoicism to modern mindfulness practices, which stress that we must cultivate presence in our everyday lives. On the other hand, this awareness of the universe's end can also inspire a deeper sense of responsibility. If we accept that our time on Earth is but a fleeting blip in the cosmic timeline, it may spur us to take greater care in shaping the future. Many ethical philosophies, such as utilitarianism or deep ecology, stress the importance of stewarding the Earth for future generations. By considering the potential end of the universe, we are reminded that our actions today have lasting consequences, not just for ourselves, but for those who will inherit this planet after us. This duality, living fully while also considering the long-term effects of our actions, forms a delicate balance. It compels us to reflect on the legacy we wish to leave. Do we aim to live in the moment, or do we focus on the greater good and the well-being of future generations? These ethical frameworks ask us to contemplate the future of humanity in the broader context of the universe itself. In recent years, we have witnessed a rapid transformation in our ability to explore the universe, a change driven by remarkable technological advancements. One of the most groundbreaking achievements in this area is the development of space-based telescopes. The launch of the James Webb Space Telescope in late 2021 marks a monumental leap in our observational capabilities. Equipped with cutting-edge infrared technology, the telescope allows scientists to peer deeper into the cosmos than ever before, providing unprecedented insights into the formation of stars, galaxies, and even the atmospheres of distant exoplanets. But telescopes are not the only tools driving this exploration. Artificial intelligence, AI, is playing an increasingly vital role in astronomical research. By utilizing advanced machine learning algorithms, scientists can now process vast amounts of data collected from space missions. AI helps identify patterns and anomalies that might otherwise go unnoticed, accelerating the pace of discovery. For example, AI has already been instrumental in the identification of new exoplanets by analyzing the light curves of stars and detecting the subtle dimming that occurs when planets transit across them. This technology has vastly expanded our ability to explore distant worlds. Moreover, the rapid advancement of propulsion technology is opening new frontiers for human space exploration. Concepts such as solar sails and ion propulsion systems are promising to revolutionize space travel. Solar sails harness the pressure exerted by sunlight to propel spacecraft, allowing them to travel without the need for traditional fuel. Ion propulsion, on the other hand, uses electric fields to accelerate charged particles beta, providing a steady and efficient thrust that could dramatically reduce travel time for missions to distant destinations, such as Mars or even farther reaches of the solar system. As these technologies continue to evolve, the possibilities for space exploration expand exponentially. The future of human presence beyond Earth may no longer be the realm of science fiction, but a tangible reality. These advancements offer us a new way to think about our place in the universe and invite us to dream about what lies beyond the edge of what we currently know. The evolution of space exploration is experiencing a groundbreaking shift, largely due to the emergence of miniaturized satellites, or CubeSats. These compact yet incredibly powerful machines are transforming our approach to studying the cosmos. Unlike traditional satellites, CubeSats can be launched in swarms, providing an unprecedented ability to collect data from multiple vantage points in space at once. The versatility and low cost of these satellites make them perfect for investigating a range of cosmic phenomena, from observing the delicate structures of our atmosphere to probing the distant corners of the solar system. Their contributions are expanding our understanding of the universe and challenging the very boundaries of our knowledge. Recent advancements in space missions have significantly broadened our understanding of the cosmos, shedding light on the origins of the universe and its most remote expanses. One of the most pioneering missions of recent years is the James Webb Space Telescope, JWST, launched in late 2021. Unlike its predecessor, the Hubble Space Telescope, which primarily captured optical and ultraviolet images, the Webb telescope is engineered to observe in the infrared spectrum. This innovative capability allows it to peer deeper into the universe's history, observing ancient galaxies as they existed mere hundreds of millions of years after the Big Bang. By penetrating the dense clouds of cosmic dust, Webb's infrared vision reveals details about the formation of the earliest stars and galaxies, offering an invaluable glimpse into the universe's infancy. The data collected by JWST is providing crucial insights into the conditions that existed during the universe's formative years. Astronomers are now able to infer the chemical makeup of these early galaxies, measure the speed at which galaxies formed, and explore the ways in which these structures have influenced the cosmic landscape over time. These revelations not only enhance our understanding of how the universe evolved, but they also provide essential clues about the fundamental laws that govern cosmic processes. Another pivotal mission that has shaped our understanding of the cosmos is the European Space Agency's Gaia spacecraft. Since its launch, Gaia has been meticulously mapping the stars within our Milky Way galaxy with an astonishing degree of precision. By measuring the positions, distances, and motions of over 1 billion stars, Gaia has produced a three-dimensional map of our galaxy. This stellar census is pivotal for scientists seeking to unravel the structure of the Milky Way and understand its interactions with nearby galaxies. As such, Gaia is playing an essential role in enhancing our broader understanding of galaxy formation and evolution, offering insights into the dynamic processes that shape the universe at large. The combined findings from missions like JWST and Gaia provide a clearer understanding of the universe's edge, where the familiar night sky begins to give way to incomprehensible vastness. These missions are also shedding light on cosmic phenomena such as dark matter and dark energy, enigmatic forces that are thought to drive the accelerated expansion of the universe. With more missions on the horizon, our perspective on the cosmos continues to evolve, bringing us closer to solving mysteries that have captivated humanity for centuries. In addition to these monumental space missions, computer simulations have become an indispensable tool for scientists exploring the vastness of the universe, especially the regions beyond the limits of our observational reach. While the observable universe is only a tiny fraction of the cosmos, defined by the distance that light has traveled since the Big Bang, advanced simulations allow researchers to peer beyond this horizon. These simulations are grounded in our current understanding of physics, incorporating fundamental laws such as gravity and radiation to model the behavior of galaxies, dark matter, and cosmic background radiation. By simulating the interactions of these forces, scientists can create vast, dynamic representations of the cosmos, offering insights into how structures might evolve over billions of years. For example, simulations allow researchers to recreate the conditions of the early universe, helping to inform theories on cosmic inflation and the distribution of galaxies. These virtual landscapes also provide a means to study processes that are otherwise impossible to observe directly, such as the complex interplay of forces at play in the formation of galaxy clusters or the effects of dark energy on the expansion of the universe. While simulations cannot replace the invaluable data collected through observational astronomy, they significantly enhance our ability to understand the universe. They allow scientists to test hypotheses that would be difficult, if not impossible, to confirm through direct observation alone. As technological advancements continue, these simulations are becoming increasingly sophisticated, allowing researchers to refine their models of the cosmos and broaden our understanding of the universe's past, present, and future. As we stand at the threshold of a new era in space exploration, several breakthroughs in technology are poised to revolutionize our comprehension of the cosmic frontier. One of the most exciting developments is the rapid advancement of artificial intelligence, AI. Modern AI algorithms can process vast amounts of data from space missions and telescopes at speeds far exceeding human capabilities. This unprecedented data processing power allows scientists to identify celestial bodies, uncover hidden patterns, and even detect signals that might indicate the presence of extraterrestrial life. AI systems are now able to scan enormous regions of space, providing insights that were previously unimaginable. The ability to analyze data at such a rapid pace allows researchers to expand the limits of our knowledge, identifying celestial phenomena and uncovering new cosmic mysteries. The ongoing integration of AI into space research is helping to push the boundaries of what we know about the universe, accelerating the pace at which we explore the far reaches of space and unravel the profound mysteries of the cosmos. Moreover, the rise of cutting-edge propulsion technologies such as ion drives and solar sails is set to radically transform the future of space travel. Unlike traditional chemical rockets, these advanced systems are capable of providing continuous thrust over extended periods. This unique feature allows spacecraft to gradually accelerate, enabling them to reach far-flung destinations much more efficiently. Imagine embarking on a journey to the outer planets or even beyond, completing the voyage in mere weeks, rather than the years it would traditionally take. These propulsion methods could dramatically alter our ability to explore the solar system, offering new possibilities for sending probes to distant moons of Jupiter or to the frigid reaches of the Kuiper Belt. In the distant future, they may even serve as a stepping stone to interstellar travel, allowing us to venture into other star systems, a prospect that until now has remained firmly within the realm of science fiction. Another frontier that holds immense promise is the next generation of space telescopes. These instruments aim to build on the legacy of the Hubble Space Telescope, pushing the boundaries of what is possible in astronomical observation. For example, the James Webb Space Telescope, with its ability to capture images in the infrared spectrum, is set to offer unprecedented views of the cosmos. Through this innovative technology, scientists will be able to peer into the atmospheres of exoplanets, searching for the building blocks of life, and exploring the early stages of galaxy formation. The insights gained from such observations could have profound implications for our understanding of life beyond Earth, possibly reshaping our perception of the universe and revealing how and where life could emerge elsewhere in the cosmos. Meanwhile, significant strides in material science are laying the groundwork for more durable, efficient, and sustainable spacecraft. Lightweight composites alongside self-repairing materials are among the innovations that could make space missions safer and more cost-effective. As these technologies evolve, the dream of establishing long-term human habitats on Mars or constructing permanent space stations in deeper regions of space is becoming increasingly plausible. Each of these advancements contributes to a growing arsenal of tools that will empower us to explore and understand the universe more thoroughly. Together, they bring us closer to answering some of humanity's most profound questions about existence, our place in the cosmos, and the possibility of life beyond Earth. The importance of international collaboration in space exploration cannot be overstated. The sheer scale of space exploration and the complexity of its challenges require a pooling of resources, expertise, and knowledge from across the globe. No single nation possesses all the specialized skills or technologies necessary to tackle the immense hurdles posed by space. Through cooperation, countries can address these challenges more effectively, sharing the costs and risks associated with large-scale scientific endeavors. One of the most compelling examples of such collaboration is the International Space Station, ISS, a joint project that brings together astronauts and scientists from numerous countries. In this unique laboratory, research in astrophysics, biology, and materials science is conducted in the weightlessness of space, yielding groundbreaking discoveries that benefit humanity as a whole. The collective efforts of space agencies like NASA, the European Space Agency, ESA, the Japan Aerospace Exploration Agency, JAXA, and Russia's Roscosmos are emblematic of how shared goals can drive scientific progress. These collaborations lead to technological advancements that have far-reaching applications beyond space exploration. Large-scale projects, such as the Large Hadron Collider and the upcoming James Webb Space Telescope, depend on contributions from scientists and engineers around the world. By exchanging ideas and data, these international teams fuel innovation, accelerating our understanding of cosmic phenomena. The ability to share research and troubleshoot problems collectively has allowed for faster and more accurate discoveries, enhancing our knowledge of the universe. These global partnerships also foster stronger diplomatic ties between nations, creating a shared sense of purpose and inspiring the next generation of explorers and scientists. As we continue to push the boundaries of human knowledge, these collaborations remind us that the quest for answers about the cosmos is a universal endeavor. It transcends borders, uniting people across the globe in our shared pursuit of discovery. In recent years, the ability to harness satellite data has revolutionized our approach to mapping the farthest reaches of space, expanding our understanding of the universe in ways that were previously unimaginable. Satellites, equipped with advanced instruments, are now able to gather an enormous range of information from distant celestial bodies, helping us uncover the hidden mysteries of the cosmos. Through direct imaging and remote sensing, these satellites can observe phenomena such as light radiation, cosmic microwave background radiation, and other key signals from across the vast expanse of space. One of the most important contributions of satellites to our understanding of the universe comes from their ability to measure the light emitted by galaxies. Instruments on board these spacecraft can analyze light spectra, which in turn reveal crucial details about the chemical composition, age, and movement of galaxies that may be billions of light years away. This ability allows astronomers to create three-dimensional maps of the universe, providing insights into the arrangement of galaxies and galactic clusters across the cosmic landscape. These findings are essential for understanding the universe's expansion, as well as the fundamental forces that govern its behavior. Satellites also play a crucial role in the study of cosmic radiation, a vital tool for exploring the early universe. For instance, the cosmic microwave background radiation, which is a remnant of the Big Bang, offers a snapshot of the universe when it was just a few 100,000 years old. Instruments like the Planck Observatory have been instrumental in detecting this faint afterglow, shedding light on the universe's early conditions, and offering clues about its growth, structure, and the underlying geometry of space itself. These advancements in satellite technology have provided scientists with the tools they need to unravel the mysteries of the cosmos, offering a deeper understanding of the universe's origins, its current state, and its potential future evolution. Moreover, satellites play a crucial role in mapping distant cosmic events such as supernova or gravitational waves. These phenomena, often invisible to the naked eye, carry profound significance in how we perceive and understand the universe. By observing them from afar, scientists can collect vital data about the life cycles of stars, the behavior of black holes, and the intricate forces at play in the cosmos. Each discovery made through satellite data brings us one step closer to solving the grand cosmic puzzle, deepening our comprehension of the vast and mysterious expanse that envelops us. Artificial intelligence, AI, is also reshaping how we approach the study of the universe, especially when it comes to managing and interpreting the immense volumes of data produced by modern telescopes and satellites. The universe is an extraordinarily complex and ever-changing entity, and our observational instruments gather staggering amounts of information about distant galaxies, cosmic radiation, and various celestial phenomena. The data generated can be overwhelming, and sifting through it manually would be an insurmountable task. This is where AI steps in as a powerful ally. It has the capacity to quickly process massive data sets, identifying patterns and anomalies that might elude human researchers. One of AI's primary roles in cosmology is its ability to enhance data analysis. Machine learning algorithms, when trained with vast data sets, can recognize specific features, such as the distinct light signatures of various stars or the faint gravitational waves produced by colliding black holes. By leveraging AI to analyze these data sets, astronomers can uncover discoveries at a speed that would be impossible using traditional methods. The rapid pace of AI-driven analysis accelerates the scientific discovery process, offering us insights into the universe far more quickly than before. This increased efficiency opens the door to exploring the deeper reaches of the cosmos, pushing the limits of our knowledge in ways that were once unimaginable. In addition to aiding in data analysis, AI also plays a key role in the interpretation of complex astrophysical models. Simulating cosmic phenomena, such as supernova explosions or the formation of galaxies, involves intricate calculations and numerous approximations. AI can assist by processing large volumes of data, learning from these datasets, and refining the models, which leads to more accurate predictions. This iterative process not only enhances our understanding of galaxy formation and evolution, but also brings clarity to some of the most critical questions in modern cosmology, such as the nature of dark matter and the expansion of the universe. As we venture farther into the cosmos, AI's collaboration with human researchers holds enormous promise. It is through this partnership that we are able to begin unraveling the mysteries of the universe and interpreting cosmic phenomena in ways that were once thought beyond our grasp. By harnessing the power of AI, we are not merely observing the universe, we are gaining a deeper understanding of its fundamental processes. This newfound comprehension not only expands our horizons, but also serves as an inspiration for future generations of scientists who will continue the quest for knowledge beyond the stars. Black holes, among the most captivating and enigmatic phenomena in the universe, offer invaluable insights into the very nature of space and time. These mysterious regions of space possess a gravitational pull so strong that nothing, not even light, can escape their grasp. This intense gravitational force arises from an immense concentration of mass within a small area, typically the remnants of massive stars that have undergone supernova explosions. The study of black holes enables scientists to confront one of the most intriguing concepts in cosmology, the boundaries of the universe. These boundaries are embodied in the event horizon, the point of no return that surrounds a black hole. Once an object crosses this threshold, it is irrevocably drawn into the black hole, unable to escape. The event horizon presents a fascinating and unsettling challenge to our understanding of space and time, as it marks the point where the known laws of physics begin to break down. The very existence of this boundary raises profound questions about the nature of reality, sparking philosophical and scientific speculation about the fabric of the universe itself. As we continue to study black holes, our understanding of their role in the cosmos grows ever more intricate. The exploration of these cosmic giants challenges our perceptions of the universe, pushing the boundaries of our scientific knowledge and offering profound insights into the deepest mysteries of existence. Through these investigations, we are not only gaining a greater understanding of black holes, but also drawing closer to answering some of the most fundamental questions about the very nature of the universe and our place within it. Black holes are among the most enigmatic and captivating phenomena in the universe, serving as both a symbol of the unknown and a testing ground for some of the most profound questions in physics. They have long captured the curiosity of scientists and laypeople alike, offering a glimpse into the deep, mysterious mechanisms that govern the cosmos. At the heart of their intrigue lies the role they play in advancing our understanding of fundamental physics, particularly the theories of relativity and quantum mechanics. When researchers turn their attention to black holes, they are not just studying objects of immense gravity and mass. They are pushing the very boundaries of our knowledge. These cosmic giants challenge everything we know about space, time, and the interaction between forces. As scientists probe deeper into their mysteries, new dimensions of the universe slowly emerge, linking black holes to some of the most elusive and baffling phenomena in astrophysics, such as dark matter and dark energy. In this sense, black holes act as gateways to the unknown, igniting our insatiable curiosity about what lies beyond the observable universe. But these celestial anomalies are not only a curiosity for theorists, they represent a true frontier for exploration. Black holes compel us to rethink what we understand about the universe's ultimate fate. Rather than viewing the cosmos as a simple collection of galaxies and stars, they prompt us to consider the universe as an intricate, interconnected web, one where the edges of our comprehension are continually tested and redefined. Among the most awe-inspiring of black holes are the supermassive varieties, which reside at the centers of galaxies. These gargantuan entities, with masses ranging from millions to billions of times that of our Sun, wield a profound influence on the cosmic landscape. Far from being passive objects, supermassive black holes actively shape their galactic surroundings. Their gravitational pull affects the movement of stars, gas, and other matter within their host galaxies. As a result, they often serve as anchors, binding together vast regions of space with an invisible force. As these black holes consume surrounding material, they unleash incredibly powerful jets of radiation, illuminating vast stretches of space. These jets are so intense that they can influence star formation, either promoting or suppressing it depending on the flow of energy and matter. In fact, the interaction between supermassive black holes and their host galaxies goes even deeper than this. It is widely believed that the growth of supermassive black holes is intricately tied to the evolution of galaxies themselves. The process is cyclical. As matter spirals into these dense centers, it forms hot, rotating disks that emit energetic radiation. This radiation can, in turn, regulate star formation within the galaxy, sometimes preventing it by expelling gas through powerful winds. The role of supermassive black holes in shaping galaxies doesn't stop there. Their influence is critical to understanding the large-scale structure of the universe. The immense gravitational fields of these black holes distort the fabric of space-time around them, warping the space in their vicinity in a way that scientists can measure. In regions where multiple black holes exert their gravitational forces, these distortions become even more pronounced. By studying the way that stars and gas move in response to these forces, astronomers can trace the distribution of dark matter, an unseen and mysterious component that makes up most of the universe's mass. Furthermore, these massive black holes may hold clues about the ultimate fate of the universe itself. Recent observations suggest that their growth and activity are closely linked to cosmic events, such as galactic mergers. These interactions not only help us understand the evolution of galaxies, but also offer insight into the broader questions of cosmic expansion and eventual contraction. As the universe continues to unfold, supermassive black holes remain essential markers, helping astronomers map the cosmos and guiding our quest to understand the nature of existence. One of the most thought-provoking issues in the study of black holes is the black hole information paradox, a concept that challenges our deepest assumptions about the universe. At the core of the paradox is a fundamental conflict between quantum mechanics and general relativity, two pillars of modern physics. The paradox centers on what happens to information, the detailed data about particles and their states, when it falls into a black hole. According to classical physics, once something crosses the event horizon, it is lost to the universe forever, as nothing, not even light, can escape the black hole's grasp. This presents a dilemma. If black holes destroy information, it would violate a core principle of quantum mechanics, which holds that information must always be conserved. This apparent contradiction has spurred numerous theories attempting to resolve the paradox. Some suggest that black holes might not destroy information at all, but could instead leak it back into the universe in some form. One possibility is Hawking radiation, a theoretical process in which black holes emit faint radiation due to quantum effects near the event horizon. These theories introduce an intriguing connection between quantum mechanics and gravitational forces, suggesting that black holes may not be just regions where gravity reigns supreme, but could also serve as conduits for information, deepening our understanding of the cosmos. If these theories hold true, they could challenge our current framework of the universe, prompting a rethinking of the very nature of reality. The ongoing debate over the black hole information paradox highlights the limitations of our current scientific knowledge, suggesting that we are still far from understanding the true nature of the universe. In many ways, this paradox opens the door to new theories and new possibilities, pushing the boundaries of what we know about the universe. As scientists continue to study black holes, they are not just investigating a specific phenomenon, but are exploring the very fabric of reality itself. This search for answers offers a glimpse into the profound complexity of the cosmos, reminding us that in the world of physics, the edges of our knowledge are often just gateways to wider horizons. Equally fascinating are the theoretical concepts of wormholes, which have captured the imagination of physicists and science fiction enthusiasts alike. Often described as shortcuts through space-time, wormholes are solutions to the equations of general relativity, first proposed by Albert Einstein. These hypothetical structures could connect two distant points in the universe, creating a tunnel-like passage that might allow for instantaneous travel between far-flung regions of space. But the idea of wormholes extends beyond mere travel. Some theories propose that these structures could serve as bridges to other universes or dimensions. The notion of a multiverse, the idea that countless universes exist, each with its own set of physical laws and constants, has fueled speculation that wormholes might connect our universe to these parallel realities. However, despite the tantalizing possibilities, wormholes remain purely theoretical. No empirical evidence has been found to support their existence, and they remain one of the most captivating yet elusive ideas in modern physics. The concept of wormholes, like that of black holes, challenges our understanding of the very nature of the universe. These theoretical constructs raise profound questions about the structure of space-time, the limits of scientific exploration, and the potential for realities beyond our own. Whether wormholes are real or merely mathematical curiosities, they serve as a reminder of the vast, unexplored reaches of the cosmos and of the infinite possibilities that lie beyond the horizon of our current knowledge. In the vast expanse of the cosmos, even as we delve deeper into the intricate tapestry of space, certain ideas remain both captivating and elusive. Among these ideas, wormholes, hypothetical structures that act as shortcuts or portals through space-time, have captured the imagination of both scientists and science fiction enthusiasts alike. These theoretical passages could allow for instantaneous travel across vast distances, potentially even between different universes. Yet, despite their allure, the scientific community faces monumental challenges when it comes to maintaining stability within these cosmic structures. Wormholes, if they indeed exist, would require the presence of something known as exotic matter, a substance with negative energy density. This exotic matter is essential to keeping a wormhole open, preventing it from collapsing under the immense gravitational forces that would otherwise seal it off. Without it, any attempt to traverse such a passage would lead to its collapse, trapping anything inside, no matter how fast it travels, rendering it impossible for even light to escape. This highlights the paradoxical nature of wormholes, where the very forces that would allow for travel across space-time also make such journeys incredibly dangerous and difficult to achieve. Still, the notion of wormholes continues to captivate scientists, who see in them the potential for groundbreaking discoveries. These cosmic shortcuts could, in theory, allow for time travel, interdimensional travel, or even connections to other realms of existence, stimulating both our scientific curiosity and our imagination. As we explore the unknown, the question remains, will we ever find a way to navigate through these cosmic doorways? While the answer is still uncertain, the pursuit itself brings us closer to unraveling the deeper mysteries of our universe, encouraging us to constantly reimagine what is possible within the realms of space, time, and reality. Black holes, another one of the universe's most enigmatic phenomena, have long been a source of both wonder and speculation. These cosmic giants are not only captivating because of their extreme gravitational forces, which warp the fabric of space-time, but also because of the tantalizing possibilities they might offer in understanding the deeper workings of the universe. One theory, in particular, suggests that black holes could serve as gateways to other universes. This theory is intertwined with the concept of wormholes and posits that black holes could act as passages between different dimensions or even entirely separate universes. According to this theory, when matter is consumed by a black hole, it may not simply disappear into nothingness. Instead, it could emerge from a white hole in a distant universe, effectively connecting different regions of space-time and offering a potential route for inter-universal travel. The mathematics behind this idea is rooted in Einstein's theory of general relativity, which explains how gravitational forces can warp space-time. Some scientists believe that the singularity at the center of a black hole, where density becomes infinite, might be a portal leading to another dimension altogether. In this scenario, matter and energy that enter a black hole might not be lost, but could traverse through an alternate reality, becoming part of a universe shaped by different physical laws. This line of thinking feeds directly into the multiverse theory, which suggests that our universe is just one of an infinite number of universes, each governed by its own set of physical rules. If black holes do indeed serve as portals to these parallel realities, they would not only expand our understanding of the universe we inhabit, but also offer glimpses into the myriad others that might exist beyond our perception. However, this remains purely theoretical, with much of the scientific community divided over the plausibility of such ideas. The difficulty lies in the fact that proving or disproving such hypotheses requires breakthroughs in advanced physics, where many of the answers may exist far beyond the reach of current experimental techniques. As scientists continue to study black holes, their status as potential conduits to other universes remains a subject of intense debate. Yet, these ideas inspire a profound sense of curiosity and wonder. The prospect of parallel universes and alternate realities challenges our understanding of space, time, and existence itself, urging us to reconsider the very foundations of reality. One concept that plays a crucial role in our evolving understanding of black holes is Hawking radiation, a theory put forth by the legendary physicist Stephen Hawking. This groundbreaking idea suggests that black holes are not, as once thought, entirely black. Instead, they emit radiation, a phenomenon driven by quantum mechanical effects occurring near their event horizons. Hawking proposed that due to the strange interactions between particles and the immense gravitational pull of the black hole, particles can emerge from what appears to be nothing. Over time, this radiation causes the black hole to slowly lose mass, a process that ultimately leads to its gradual evaporation. The implications of Hawking radiation are far-reaching. For one, it suggests that black holes are not eternal, as many had assumed. Instead, they are temporary structures within the cosmos, subject to the same laws of physics that govern all matter and energy. This challenges the conventional view of black holes as final endpoints in the universe, cosmic traps from which nothing can escape. Rather, they may represent an intermediate stage in the evolution of cosmic objects, eventually giving way to new forms of matter and energy. The discovery and study of Hawking radiation would not only reshape our understanding of black holes, but also provide crucial insights into the fundamental laws of physics. By exploring this intersection between general relativity and quantum mechanics, scientists hope to unlock the mysteries of space, time, and the very structure of the universe. Furthermore, the detection of Hawking radiation, though still beyond our current technological capabilities, could open new doors in our understanding of the cosmos. It might offer clues about the origins of the universe, the nature of dark matter, and even the future fate of cosmic structures. This brings us to the elusive concept of dark matter, a mysterious substance that, despite being invisible and undetectable through traditional means, plays a critical role in shaping the universe. Dark matter makes up about 27% of the total mass energy content of the cosmos, yet it does not emit, absorb, or reflect light, making it virtually invisible to current observational instruments. Its existence is inferred primarily through its gravitational effects on visible matter, such as stars and galaxies, suggesting that it exerts a significant influence on the structure and behavior of the universe. One of dark matter's most significant contributions is in the formation of galaxies. Early in the history of the universe, slight fluctuations in density led to the clumping of matter, with dark matter providing the essential framework around which visible matter could accumulate. These dense regions eventually gave rise to the galaxies we observe today. Without dark matter, the formation of galaxies and the large-scale structure of the universe as we know it would likely have been impossible. Yet, despite its profound influence, dark matter remains one of the greatest mysteries of modern science, with its true nature still largely unknown. In the grand scheme of the universe, dark matter serves as a crucial, albeit unseen, architect of cosmic evolution. As scientists continue to investigate its properties, they may soon uncover even deeper layers of the universe's hidden structure, unveiling a cosmos far more complex and mysterious than we could ever have imagined. The journey into these unknowns promises to push the boundaries of human knowledge, leading us to new and exciting revelations about the nature of reality itself. Without the gravitational pull of dark matter, galaxies would face immense difficulty in holding their stars and gas together, leading to a cosmos that could look strikingly different from what we observe today. In fact, it might be a universe with far less structure, with galaxies scattered in a more chaotic and less cohesive manner. Dark matter doesn't just shape the galaxies themselves. It plays a pivotal role in the large-scale architecture of the universe. It is the unseen hand that determines how galaxy clusters and superclusters form, weaving a vast, intricate network that spans the entire cosmos. This cosmic web, primarily constructed by dark matter, reveals itself in the clustering patterns of galaxies. Instead of galaxies being spread evenly across space, they tend to congregate along the filaments of dark matter, outlining a massive, interconnected structure that maps out the gravitational influence of this invisible force. These filamentary structures are not just cosmic curiosities. They are essential to understanding the very nature of the universe's expansion. By examining the way galaxies align along these filaments, scientists gain insights into the underlying forces that guide the evolution of the cosmos. This web offers crucial clues about how galaxies move, how they interact, and how the universe itself is growing. It also provides a framework for understanding phenomena like gravitational lensing, a process that occurs when light from faraway galaxies passes near enormous clusters of matter, only to be bent by the gravitational pull of that matter. This bending reveals not only the presence of mass, but also its distribution, offering indirect evidence of dark matter. Gravitational lensing allows scientists to map out the presence and amount of dark matter in a way that would be impossible through direct observation. In this way, dark matter is not just theorized to exist, it is proven through the bending of light, a phenomenon that brings into sharper focus the universe's expansion and the unseen forces at play. As we continue to peer deeper into these cosmic phenomena, we are led to appreciate the complexity of the universe's structure and the vital role that dark matter plays in shaping everything around us. Another enigmatic component of the universe is dark energy, which comprises roughly 70% of the total energy density of the cosmos. It is believed to be the force responsible for the accelerated expansion of the universe, a concept that gained significant traction in the late 1990s. Observations of distant supernova revealed something unexpected. The expansion of the universe was not slowing down, as had long been assumed, but rather speeding up. This realization defied traditional cosmological models and prompted the introduction of dark energy as a possible explanation for this acceleration. One of the leading theories about dark energy suggests that it is a constant energy density that permeates all of space, often referred to as the cosmological constant. This idea was originally proposed by Albert Einstein in the 1910s when he introduced the cosmological constant into his equations of general relativity. At the time, Einstein used it to maintain a static model of the universe. a notion that was later discarded when it was discovered that the universe was, in fact, expanding. However, the unexpected acceleration of the universe's expansion revived interest in the cosmological constant. Now, scientists theorize that dark energy is the force that drives galaxies apart, pushing the universe to expand at an ever-increasing rate. Alternatively, some researchers propose that dark energy is not a constant, but rather a dynamic force that evolves over time and space. This theory, known as quintessence, posits that dark energy can vary in strength, possibly even influencing the expansion of the universe differently at various points in time. Quintessence provides a more flexible framework for understanding the cosmic expansion, suggesting that the relationship between dark energy, matter, and gravity could be far more intricate and interconnected than previously thought. Yet, not all theories rely on the concept of dark energy itself. Some researchers argue that the acceleration of the universe could be explained by a fundamental revision of our understanding of gravity. They suggest that the laws of gravity, as described by Einstein, might need to be adjusted to account for the observed cosmic expansion. This perspective, while radical, opens up new avenues for thinking about the universe's evolution and challenges our existing theories in profound ways. These competing ideas about dark energy, whether it is a constant force, a dynamic entity, or something else entirely, represent the forefront of cosmological research. As scientists continue to collect data and refine their models, the mystery of dark energy remains one of the most tantalizing puzzles in modern science. The answers we uncover will be instrumental in revealing the ultimate fate of the universe and in deepening our understanding of the very fabric of reality itself. The task of detecting and measuring dark matter is one of the most formidable challenges in modern astrophysics. This elusive substance does not interact with light in the same way that ordinary matter does. It neither emits, absorbs, nor reflects light, making it completely invisible to traditional observation methods. As a result, scientists have developed a variety of ingenious techniques to indirectly detect dark matter by studying its gravitational effects on visible matter. One of the most telling clues comes from the rotation of galaxies. When astronomers observe how galaxies spin, they notice something strange. The outer regions of galaxies rotate much faster than would be expected based solely on the visible matter. According to the laws of gravity, the stars and gas at the outer edges should not have enough gravitational pull to move at such high speeds unless there is an unseen mass exerting additional force. This unseen mass is believed to be dark matter. Another key piece of evidence for dark matter comes from studying galaxy clusters. By analyzing the motions of galaxies within these clusters, scientists can calculate the total mass of the cluster. However, the observed mass is far less than what would be needed to explain the high velocities at which galaxies move. This discrepancy suggests the presence of an unseen mass, again, thought to be dark matter, that is influencing the gravitational dynamics of these clusters. Furthermore, scientists can use gravitational lensing to probe the distribution of dark matter. When light from distant objects, such as other galaxies, passes near a massive galaxy cluster, it bends due to the gravitational influence of that cluster's mass. This bending, often compared to a cosmic magnifying glass, provides a way to map out the distribution of dark matter, revealing its presence even though it is otherwise invisible. In sum, while dark matter remains one of the greatest mysteries in modern science, the evidence for its existence is compelling. Its effects on the rotation of galaxies, the motion of galaxy clusters, and the bending of light all point to the presence of this invisible substance. As our understanding of dark matter deepens, we move closer to unlocking the secrets of the cosmos and the hidden forces that shape the universe. Experiments conducted in underground laboratories are designed to directly detect the elusive particles of dark matter. These facilities are equipped with highly sensitive detectors buried deep beneath the Earth's surface to shield them from cosmic rays and the persistent radiation of the background. The reasoning behind this approach is straightforward. If dark matter particles interact with ordinary matter, even if the interaction is exceedingly rare, they might create signals that scientists could detect. Different techniques are employed in the search for these elusive particles, one of the most fascinating being the detection of tiny recoil movements in heavy atomic nuclei. These subtle shifts could offer a window into the properties of dark matter, shedding light on a phenomenon that has long eluded direct observation. In addition to these efforts, researchers also rely on advanced simulations to deepen our understanding of dark matter's role in the evolution of the universe. By modeling the gravitational interactions that occur across vast cosmic distances, scientists can predict how dark matter affects the formation and distribution of galaxies over time. These predictions allow us to peer further into the cosmos, offering a clearer picture of how dark matter might shape the very structure of the universe itself. Through a combination of detection methods, gravitational observations, and sophisticated modeling, the scientific community is gradually piecing together the puzzle of dark matter, inching closer to uncovering the secrets of this enigmatic substance. Dark energy stands as one of the most perplexing and captivating mysteries in modern cosmology. It is a force that exerts a profound influence on the universe, accounting for approximately 70% of its total energy content. Dark energy plays a pivotal role in the universe's ongoing expansion. Initially, scientists believed that gravitational forces would slow down the universe's expansion over time. Yet, the discovery of dark energy has flipped that assumption on its head, revealing instead that the expansion of the universe is accelerating. This revelation has fundamentally altered our understanding of cosmic destiny, offering a new, unexpected perspective on the universe's long-term fate. As dark energy continues to dominate the energy composition of the universe, it will likely dictate the direction of the cosmos in the distant future. Current theories suggest that if dark energy remains constant and unchanging, the universe will continue to expand at an ever-accelerating pace. This scenario could lead to a future in which galaxies drift farther and farther apart, eventually creating a cold, sparse, and desolate cosmos, a state commonly referred to as the Big Freeze. In this distant future, stars will either burn out or drift away, leaving behind a dark and silent universe where the light of creation has faded away. Yet, alternate theories suggest that dark energy could evolve over time, leading to a vastly different fate for the universe. Some hypotheses propose that dark energy may become more powerful, intensifying its effect on the fabric of space-time. This scenario could lead to what is known as the Big Rip, a catastrophic event where the force of dark energy becomes so overwhelming that it tears apart galaxies, stars, planets, and even the very structure of space itself. The Big Rip would mark a dramatic and violent end to the universe as we know it, annihilating everything in its path. As of now, we have only scratched the surface of understanding dark energy, and its far-reaching consequences for the cosmos remain an open question. Ongoing research facilitated by cutting-edge telescopes and extensive surveys is essential for unraveling the secrets of dark energy. By studying distant supernovae and galaxy clusters, scientists hope to gain a better understanding of how dark energy shapes the universe, ultimately helping to determine the ultimate fate of all cosmic matter. These explorations are vital for advancing our comprehension of one of the most perplexing and influential forces in the universe. Theories about dark matter have radically transformed our understanding of the universe, particularly in regard to its structure and the concept of its boundaries. Traditional cosmological models suggested that the universe was made up primarily of visible matter, stars, planets, and galaxies that we could observe through our telescopes. However, dark matter, an invisible and enigmatic substance, is now believed to account for approximately 27% of the total mass energy content of the universe. This realization challenges existing models, implying that the universe is far more complex than previously imagined. Dark matter does not emit, absorb, or reflect light, making it exceedingly difficult to detect directly. Instead, our knowledge of it is based primarily on its gravitational effects. Observations show that galaxies spin at such high speeds that, if only visible matter existed, they would be torn apart by centrifugal forces. Dark matter is thought to provide the gravitational glue that binds galaxies together, allowing them to remain intact despite the immense forces acting upon them. This discovery forces us to reconsider not just what our universe is made of, but also how it is structured, especially when it comes to the question of its boundaries. These new insights into dark matter lead to intriguing questions. What happens at the edges of the universe? Conventional models have framed the universe as a vast expanse with a well-defined edge, but dark matter suggests a more intricate and potentially infinite structure. New models incorporating dark matter propose that the universe might not have a hard, well-defined boundary. Instead, it may exhibit a continuous, interwoven fabric of gravitational influences that stretches far beyond our current observational capabilities, beyond what we can see or even comprehend. As scientists continue their investigations into dark matter, they are uncovering fascinating revelations about the very architecture of the universe, particularly in relation to the unseen forces that govern the formation of galaxies. One of the most striking pieces of evidence comes from measurements of the speed at which stars and gas orbit the centers of galaxies. In traditional models, the farther a star or gas cloud is from the center of a galaxy, the slower its orbital speed should be, much like the way planets in our solar system move more slowly the farther they are from the sun. However, this is not what astronomers observe. Instead, they find that stars at the outer edges of galaxies are moving just as fast as those closer to the center. This anomaly is a key piece of the puzzle, leading scientists to conclude that a hidden force, dark matter, must be exerting its gravitational influence on the galaxy, stabilizing it and preventing it from flying apart. Through ongoing experiments, observations, and simulations, scientists are not only unmasking the nature of dark matter, but are also revisiting fundamental questions about the structure and fate of the universe. The more we learn, the clearer it becomes that the universe is far more complex and mysterious than our current models can explain, and dark matter is at the heart of this cosmic enigma. However, observations spanning several decades have revealed a fascinating and unexpected consistency in the velocities of objects within galaxies. Even at distances far from a galaxy's center, these objects continue to move at remarkably high speeds, defying predictions based on the observable mass. This surprising phenomenon strongly suggests that there must be a significant amount of unseen mass lurking beyond the visible matter we can detect. Matter that does not emit or reflect light, like stars, gas, or dust. Scientists have proposed that this hidden mass could be the elusive dark matter, a mysterious substance that doesn't interact with electromagnetic radiation. This makes dark matter undetectable by traditional observational techniques. Despite its invisibility, dark matter is believed to account for approximately 25% of the universe's total mass and energy content. The discovery of this unseen mass challenges our understanding of the cosmos, revealing that much of the universe's mass lies beyond our capacity to directly observe it. The implications of dark matter's existence are profound. It acts as a kind of gravitational glue, holding together galaxies and clusters of galaxies. Without it, these vast cosmic structures would not be able to remain intact. The force exerted by dark matter helps shape the formation and evolution of galaxies over cosmic timescales, allowing them to remain cohesive even as they spin at incredible speeds. Researchers have discovered that the rotation curves of galaxies, how the speed of stars and gas changes with distance from the galactic center, flatten out at large distances. This flattening is not consistent with what would be expected if only visible matter were present. Instead, it hints at the presence of a dark matter halo, a vast, invisible region surrounding galaxies that exerts its gravitational influence. This groundbreaking realization has revolutionized our understanding of cosmic structure, revealing that the universe may be dominated not by the visible matter we see, but by forces that remain completely elusive to our current observational tools. Understanding galactic rotation curves not only provides compelling evidence for the existence of dark matter, but also sparks deeper questions about the fundamental nature of reality. What exactly is dark matter made of? Are there other forces at play in the universe that we have yet to identify? Each new discovery, no matter how small, opens up vast avenues for further exploration, keeping astronomers and physicists alike continually engaged in the quest to unravel the mysteries of the universe. Dark matter and dark energy, Two of the most enigmatic components of the cosmos offer tantalizing clues about the fabric of reality itself, even though we are still far from fully understanding them. Though fundamentally different in nature, dark matter and dark energy are believed to be intertwined in a way that could significantly influence the universe's structure and ultimate fate. Dark matter is a form of matter that doesn't interact with light or other forms of electromagnetic radiation. Because of this, it is invisible and can only be detected through its gravitational effects. It acts as the scaffolding upon which galaxies and galaxy clusters are built, exerting a pull that binds these structures together. Without dark matter, galaxies would not hold their shape, and galaxy clusters would fly apart. Dark energy, on the other hand, is a force that works in direct opposition to dark matter. While dark matter pulls matter together, dark energy pushes it apart. It is the mysterious force behind the accelerated expansion of the universe, causing galaxies to move away from each other at an ever-increasing rate. As scientists continue to probe the farthest reaches of the universe, they are investigating how dark matter and dark energy interact. One intriguing hypothesis is that fluctuations in the density of dark matter could influence the behavior of dark energy. For example, regions with higher dark matter density might experience a reduced effect from dark energy, leading to areas of slower expansion. This interaction could give rise to regions of space where the expansion of the universe behaves in ways that we don't fully expect. Understanding these forces and their interplay could provide us with insights into the very fabric of space-time itself. If dark matter and dark energy are linked in ways that we do not yet comprehend, they could hold the answers to some of the most profound questions about the universe. What is the nature of gravity? How do cosmic structures evolve over time? And what is the ultimate fate of the universe? These are questions that we are only beginning to approach. And as technology advances, the mysteries of dark matter and dark energy continue to unfold. At the very edges of our observable universe, we encounter the concept of cosmic horizons, limits to what we can observe due to the finite speed of light and the age of the universe. These horizons are not physical barriers, but rather represent the boundaries of what we can see based on the time it takes for light to travel across the vast distances of space. As we peer into the cosmos, we are effectively looking back in time, seeing light from distant galaxies that has taken billions of years to reach us. Because of this, there are vast regions of the universe whose light has not yet had the chance to reach us. The observable universe, defined by this boundary, extends approximately 13.8 billion light-years from Earth. This distance is directly tied to the age of the universe and the time since the Big Bang. Beyond this threshold lies an expanse of space that remains beyond our view, since light from those regions has not had enough time to reach us. The realization that there may be an infinite expanse of unobservable cosmos beyond our reach is one of the most humbling aspects of our understanding of the universe. In addition to the observable universe, we also encounter the concept of the event horizon, particularly in relation to black holes. These event horizons represent another type of cosmic boundary. At these points, the gravitational pull of a black hole becomes so intense that not even light can escape. Anything that crosses the event horizon is doomed to be pulled into the singularity at the center of the black hole. Event horizons mark the ultimate point of no return, where the laws of physics as we understand them break down. As we explore these boundaries, whether the cosmic horizons marking the limits of our observable universe or the event horizons of black holes, we are reminded of the vastness of the cosmos and the many mysteries it still holds. Understanding these frontiers is central to unraveling the complex and awe-inspiring story of our universe's evolution. The vast and mysterious expanse of the cosmos is a topic that continues to captivate the human imagination. As we venture beyond our planet and seek to understand the true nature of the universe, we come face to face with profound limits. Limits that not only shape our observations, but also push the boundaries of what we can truly know. One such limit is the cosmic horizon, a boundary that marks the furthest reach of the observable universe. This horizon, though invisible to the naked eye, is essential in understanding the structure and the vastness of the cosmos. It signifies the point beyond which light, traveling at a finite speed, has yet to reach us since the birth of the universe itself. Thus, it encapsulates both the limitations of our observation and the tantalizing mystery of what may lie beyond. In exploring the cosmic horizon, we not only confront the limits of our knowledge, but also gain a deeper appreciation of the universe's design. It highlights the critical role of light and time in shaping our observations, reminding us that much of the universe remains hidden from our sight. Yet, even as we confront this boundary, our curiosity is fueled by the tantalizing question of what exists beyond it. The idea of a cosmic horizon invites us to reflect on our place in the cosmos, nudging us to consider how far our understanding can truly reach. It stirs a sense of wonder about the mysteries that lie just beyond our observational grasp, urging us to continue our quest for deeper cosmic knowledge. Equally fascinating is the concept of an infinite universe. While the cosmic horizon is a limit to our observations, the notion of an infinite cosmos suggests a boundless expanse, one that stretches endlessly in every direction. If the universe is indeed infinite, there would be no edge or boundary to the vastness of existence. This would imply an endless array of galaxies, stars, and perhaps even planets scattered throughout the expanse of space. Such a notion challenges our conventional understanding of the universe, raising profound questions about the very nature of reality and existence itself. How do we comprehend a cosmos without boundaries, where space and time seem to stretch into infinity? The intersection of the cosmic horizon and the concept of an infinite universe reveals a fascinating paradox. While the cosmic horizon defines the limits of what we can observe, it does not definitively dictate the size or the nature of the universe itself. In fact, many cosmologists posit that the universe could very well be infinite, even though only a finite portion of it is accessible to us through observation. This creates a tension between what we can observe and what may exist beyond that observable boundary. The horizon becomes both a practical limitation and a philosophical gateway, encouraging us to ponder the unseen realms of the universe. At the heart of this cosmic mystery lies the expanding nature of the universe, a discovery that has reshaped our understanding of the cosmos. Identified through observations of distant supernovae, the accelerated expansion of the universe suggests that galaxies are receding from one another at an increasing rate. This dynamic behavior challenges the notion of a static universe and points to a cosmos that is continuously stretching and evolving. The more we observe, the more we realize that the idea of a fixed boundary becomes increasingly blurred. As galaxies recede at faster speeds, some may eventually move beyond our observational reach, creating a sense of isolation within our cosmic neighborhood. In this expanding universe, there is no clear edge. Instead, space itself is continuously stretching, making the true scale of the universe difficult to comprehend. The cause of this accelerated expansion is attributed to a mysterious force known as dark energy, which accounts for about 70% of the universe's total energy content. Dark energy behaves in ways that defy our conventional understanding of gravity and matter. How does this enigmatic force work? Is it constant, or does it change over time? What impact does it have on the overall structure and fate of the universe? These questions remain at the forefront of modern cosmological inquiry, as scientists strive to understand the true nature of dark energy and its role in shaping the universe's future. As we contemplate the implications of this accelerated expansion, we are compelled to rethink fundamental ideas about the universe's past and its eventual fate. With each new discovery, astronomers and cosmologists gather valuable clues that help unravel the mysteries of the cosmos. The rapid pace of cosmic expansion presents both challenges and opportunities for a deeper understanding of the universe. It is a reminder that the exploration of our universe is not only about observing distant objects, but also about investigating the underlying forces that drive its evolution. The discovery of the expanding universe, a key milestone in modern cosmology, fundamentally altered our perception of the cosmos. The first clues to this expansion came in the early 20th century, when astronomer Edwin Hubble observed that distant galaxies were moving away from us. This phenomenon, known as redshift, occurs when light from distant objects is stretched as it travels through space, shifting it toward the red end of the spectrum. Hubble's groundbreaking observations demonstrated that not only was the universe expanding, but that the farther away a galaxy is, the faster it appears to be receding from us. This observation set the stage for decades of research that would confirm the ongoing expansion of the cosmos. One of the key pieces of evidence supporting this expansion model came in the mid-20th century with the detection of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation, which fills the entire universe, provides a snapshot of the cosmos when it was just 300,000 years old. Detailed measurements of this radiation made by satellites such as the Wilkinson Microwave Anisotropy Probe have provided invaluable insights into the early conditions of the universe, shedding light on its expansion and the forces at play during its infancy. Further refinements to our understanding of cosmic expansion came with the discovery of dark energy. This mysterious force was first inferred in the late 1990s through observations of distant supernovae. Astronomers noticed that these stellar explosions appeared dimmer than expected, suggesting they were farther away than initially thought. This discovery indicated not only that the universe was expanding, but that the rate of expansion was actually accelerating over time, an unexpected and puzzling finding that continues to challenge our understanding of the cosmos. Together, these observations paint a coherent picture of a dynamic universe that is far from static. From Hubble's initial observations of galaxy redshift to the detection of cosmic microwave background radiation and the discovery of dark energy, each piece of evidence has contributed to a deeper understanding of the universe's ever-evolving nature. The expanding universe is not merely a static process, but a vibrant and continuously unfolding story that challenges our perceptions and shapes our understanding of the cosmos. As we cross the boundary of the cosmic horizon in our imagination, we enter a fascinating thought experiment. The cosmic horizon represents the limit of our observable universe, the furthest distance that light has had time to travel since the universe's birth. Should we somehow be able to cross this horizon, we would witness an extraordinary expansion of our observational field. The galaxies, quasars, and cosmic phenomena that were once beyond our reach would come into view, offering a glimpse of the universe as it was billions of years ago. We would be able to see the formation of new stars and galaxies, events that occurred long before the light we see today began its journey across the cosmos. In crossing this boundary, we would be given a unique window into the past, allowing us to observe the very processes that shaped the universe into the vast, intricate structure we observe today. The cosmos is a vast and endlessly evolving mystery, one that continues to beckon us toward greater discovery. While our ability to observe and understand the universe is constrained by the limits of time, light, and distance, the questions it raises about existence, time, and space drive us ever forward. The cosmic horizon, the expanding universe, and the mysterious force of dark energy invite us to explore, question, and dream of a cosmos that is far more complex and magnificent than we could ever fully comprehend. Crossing the cosmic horizon could revolutionize our understanding of space, time, and the very fabric of the universe. The universe as we know it is in a state of continuous expansion, with some galaxies receding from us at speeds exceeding that of light due to this very process. This expansion is not a simple movement, but a dynamic stretching of space itself. If we were to transcend our current limitations and explore regions of the universe where the expansion rate allows us to witness objects previously hidden from our view, we could encounter phenomena that challenge the very foundations of what we know. Such an event would alter our perception of the universe's size, structure, and the boundaries of our observable reality, raising profound questions about the unknown realms that lie beyond. One of the most intriguing implications of exploring beyond the cosmic horizon is the potential encounter with new forms of matter, or even dark energy, currently elusive to direct observation. These mysterious entities govern much of the universe's behavior, but remain largely invisible. Their existence has profound implications for our understanding of the forces that shape our universe, including the expansion itself. While we are grounded in our current perspective, the very possibility of crossing this barrier invites curiosity and sparks questions about the nature of existence on a cosmic scale. At the core of our cosmic exploration lies the rate of the universe's expansion, a fundamental aspect of cosmology that not only defines the current state of the universe, but also predicts its eventual fate. Since the Big Bang, the universe has been expanding, with galaxies moving further apart as space itself stretches. The rate at which this expansion occurs is quantified by a value known as the Hubble constant, which informs us about how quickly galaxies are receding from one another based on their distance from Earth. However, this is not merely a statistic. It carries deep implications for the future of the cosmos. The expansion of the universe is driven in large part by a mysterious force known as dark energy. Initially, the universe's expansion was believed to be slowing, but observations soon revealed a surprising acceleration. This acceleration is powered by dark energy, which is thought to make up a significant portion of the universe's total energy content. As the universe continues to expand, galaxies will be increasingly separated, eventually leading to a scenario known as the Big Freeze. In this future, the universe will become increasingly cold and empty. Stars will burn out, and galaxies will drift apart into isolation, leaving behind a vast, dark, and lifeless expanse. Yet there are other possible fates for the universe. If, for some reason, the expansion were to slow down or reverse due to gravitational forces, the universe could collapse in a big crunch, with all matter returning to a dense singularity. While this scenario remains a topic of theoretical speculation, current evidence strongly suggests that the universe is on an accelerating expansion trajectory, driven by the enigmatic dark energy, making the Big Crunch scenario increasingly unlikely. Instead, the accelerating expansion points towards a future where galaxies drift apart indefinitely, leaving an ever more isolated and cold cosmos. The space-time continuum, a cornerstone of modern physics, is essential to understanding not just the mechanics of the universe, but also its very structure. Space and time, once thought to be independent of one another, are now understood to be interwoven into a four-dimensional fabric. This concept suggests that events are not only located in space, but are also situated within a complex, interconnected framework of time. This intertwining raises profound questions about the limits of our universe and the nature of space itself. The Big Bang Theory, which posits that the universe originated from an intensely hot and dense state approximately 13.8 billion years ago, suggests that space itself has been stretching since the very first moments of creation. As the universe expands, it raises the question, what lies beyond the observable boundaries? The edge of the universe, if such a thing exists, is not a solid wall, but a shifting, fluid concept, constantly moving as space continues to stretch. This challenges our traditional understanding of boundaries and calls into question the very nature of the universe's edge. The notion of a finite yet unbounded universe presents a paradox. Imagine the surface of an inflating balloon. As it expands, every point on the surface moves away from every other point. However, there are no true edges or boundaries to the surface itself. This analogy helps us understand the universe. While it is expanding, it may not have a defined edge in the conventional sense. Instead, it could curve back on itself, creating a closed structure with no definitive end. This idea leads to exciting possibilities, such as alternate dimensions or even the concept of a multiverse, vastly expanding our understanding of what might exist beyond our observable reality. The implications of these ideas challenge our perceptions of the universe and our place within it, inviting deeper questions about the nature of existence and what might lie beyond the cosmic horizon. Such inquiries drive ongoing research in cosmology and fuel the fascination that keeps humanity engaged with the mysteries of the cosmos. Albert Einstein's theories of relativity, particularly his general theory of relativity, revolutionized our understanding of the universe and the forces at work within it. Developed in the early 20th century, these theories changed the way we perceive gravity. Instead of viewing gravity as a simple force pulling objects together, Einstein proposed that gravity is the result of the curvature of space-time itself. Massive objects, such as stars and planets, warp the fabric of space and time around them, and this warping leads to what we perceive as the force of gravity. This new understanding of gravity has profound implications for cosmology, which seeks to understand the universe's origins, evolution, and ultimate fate. The curvature of space-time helps explain the behavior of galaxies, the motion of celestial bodies, and the phenomena observed in the cosmos. Rather than viewing gravity as a simple interaction between masses, we now understand it as a complex force that influences the flow of time itself and shapes the very structure of the universe. Einstein's equations allowed scientists to model a wide array of cosmic phenomena, from the dynamics of an expanding universe to the formation of black holes and neutron stars. One of the most significant predictions stemming from general relativity was the realization that the universe itself is expanding. This prediction was confirmed through observations made in the 20th century, which revealed that galaxies are moving away from each other, validating Einstein's theory and leading to the understanding that the universe began with the Big Bang. This discovery has not only provided insight into the age of the universe, around 13.8 billion years, but also solidified the concept of an expanding universe that continues to evolve. It is this ongoing expansion that shapes our understanding of the cosmos and drives the search for answers to some of the universe's most profound questions. Furthermore, Albert Einstein's groundbreaking insights have been instrumental in shaping the course of modern astrophysics, particularly in the exploration of dark matter and dark energy, two of the most elusive and mysterious components of our universe. These enigmatic forces, which together make up a significant portion of the cosmos, interact with space-time in ways that continue to challenge and expand our understanding. As they twist and warp the very fabric of space, these phenomena push the boundaries of current scientific inquiry, sparking ongoing research and theoretical explorations that persist to this day. When we reflect on Einstein's contributions, we begin to uncover a much richer and more complex narrative of the universe, one in which gravity, time, and the very structure of space are intricately interwoven. The fabric of space-time, as Einstein first proposed, forms the cornerstone of modern cosmology, offering a framework through which we can understand the vast, dynamic universe in which we live. This conceptual leap has opened up new avenues for exploration, allowing scientists to examine the intricate connections between mass, energy, and the geometry of space itself. Time, in particular, plays a pivotal role in this understanding. The nature of time and its relationship with the universe is not merely a philosophical question, but a fundamental part of how we perceive and interpret the cosmos. Time and space are no longer seen as separate entities, but as a unified, four-dimensional continuum, space-time. This groundbreaking concept has fundamentally altered our approach to everything from the motion of planets to the very structure of the universe itself. In this four-dimensional tapestry, events are not just defined by where they occur in space, but also by when they take place, marking a profound shift in how we understand the nature of reality. The age of the universe, currently estimated to be around 13.88 billion years, provides a critical lens through which we can assess the limits of our observational capacity. Light traveling at a finite speed has its own limitations, and when we look out into the cosmos, we are essentially peering back through time. The observable universe, the portion we can see and study, extends only as far as the light from distant galaxies has had time to reach us since the Big Bang. This means that while the universe itself may extend far beyond the limits of our current observations, our understanding of its total size is constrained by the finite speed of light and the time that has elapsed since the universe began. As the universe continues to expand, the distance that light can travel also increases, further pushing the boundaries of what we can observe. This expansion also affects our understanding of cosmic structures that lie beyond our current reach. While we can detect the faint cosmic microwave background radiation, a relic of the early universe, there are regions of space that lie beyond this visible horizon, areas we will never directly experience. This phenomenon defines the limits of our observational power and illustrates the central role that time plays in shaping the boundaries of human knowledge. In this sense, time serves both as a guide and a boundary. It not only defines the extent of our observations, but also shapes the theories and models that scientists develop to understand the universe. As researchers continue to explore the relationship between time, space, and the expanding universe, they uncover deeper layers of understanding, insights that both challenge and inspire us to think more profoundly about the cosmos. These discoveries ignite a sense of wonder about what may lie beyond the visible horizon, spurring our curiosity to look further and deeper into the unknown. The fabric of space-time itself is a complex and intricate tapestry, woven from the interactions of gravity, mass, energy, and time. This fabric dictates how celestial bodies move, how light travels, and how the very shape of the universe evolves. When we discuss alterations to this fabric, we enter the realm of phenomena like gravitational waves, black holes, and the ongoing expansion of the universe. Each of these events not only offers valuable clues about the nature of the objects involved, but also provides hints at deeper mysteries concerning the universe's limits and structure. For example, when massive objects like black holes distort the fabric of space-time around them, they generate ripples, gravitational waves that propagate outward through space. These waves, which can be detected by highly sensitive instruments on Earth, offer a direct way to study events that occurred billions of light years away. By analyzing these ripples, scientists can learn not only about the dynamics of gravitational interactions, but also about the properties of distant regions in the universe, potentially even revealing the existence of structures or phenomena that lie far beyond our observable reach. Similarly, dramatic events like supernovae, where massive stars explode in spectacular bursts of energy, also cause distortions in space-time. These explosions leave behind immense voids that warp the very fabric of the universe. Studying these cataclysmic events helps scientists to better understand the relationships between matter and energy, offering potential clues to what lies at the edges of our observable universe. Through these cosmic phenomena, we inch ever closer to deciphering what may exist beyond the limits of our vision. Moreover, the ongoing expansion of the universe provides further clues about the ultimate fate of the cosmos. As space-time stretches, scientists are gaining new insights into whether the universe is flat, open, or closed, each scenario offering a different vision of the universe's future. Will it continue to expand forever, eventually reaching an end in a cold, dark infinity? Or will it collapse back in on itself, perhaps leading to a big crunch? Or might it eventually reach a state of equilibrium, neither expanding nor contracting? These questions not only reveal the universe's present structure, but also hint at its long-term fate. The question of what lies at the edge of the universe has profound implications, not only for our understanding of cosmic boundaries, but for the very nature of reality itself. Could the edge of the universe be a gateway to regions we cannot yet comprehend, or perhaps to a multiverse, a collection of universes beyond our own? This idea, once the stuff of science fiction, is now a serious topic of discussion among theoretical physicists. The absence of any clear boundary or edge to the universe challenges our conventional understanding of space and time, suggesting that the universe may be far more complex and interconnected than we have previously imagined. In classical cosmology, we often picture the universe as a finite entity, a bounded realm with a beginning and an end. Yet, if the universe extends infinitely in both space and time, the implications are profound. The very concept of a boundary vanishes. Space and time become continuous, without limits, raising fundamental questions about the nature of existence itself. Is the universe truly infinite, or is it part of a greater, more intricate structure, perhaps even a multiverse? Without edges, every point in the universe might be connected to every other point, transitioning seamlessly through time and space. Philosophically, these ideas spark deep reflections about the meaning of existence. If the universe is unbounded, does this imply that reality itself is without end, without resolution? And what of time? If it extends infinitely backward and forward, does it mean that every event is somehow predetermined or interconnected? Does this suggest a cosmic tapestry where all events are linked, shaping a unified whole, rather than isolated, independent moments? Such considerations provoke profound questions about free will, destiny, and our place in the grand scheme of things. As we continue to explore these ideas, we not only seek to understand the universe more fully, but also confront deeper questions about existence, purpose, and the nature of reality. Through the lens of Einstein's theories and the mysteries of space-time, we begin to see that the universe is not just a collection of stars and galaxies, but a dynamic, interconnected whole, one that challenges our understanding of the very fabric of existence. The idea of exploring the boundaries of the universe forces us to reconsider the very nature of human existence. It compels us to reflect on our role in an ever-expanding cosmos. While individual lives might appear small in the grand scale of the universe, they are part of a much larger, intricate system that is in constant motion. This interconnectedness offers a profound sense of meaning. Even the most seemingly insignificant actions, when viewed from a cosmic perspective, contribute to the unfolding story of the universe itself. In this way, we are not passive observers, but conscious participants in a boundless reality that constantly evolves. Recent breakthroughs in quantum gravity have paved the way for a deeper understanding of the universe's boundaries, a concept that has intrigued scientists for generations. At the heart of this exploration lies the task of reconciling two pillars of modern physics: general relativity, which governs the force of gravity on a large scale, and quantum mechanics, which describes the behavior of particles at the smallest scales. The attempt to merge these two theories has already begun to reshape our understanding of space, time, and the universe itself, revealing profound insights that were previously inconceivable. One of the most groundbreaking developments to emerge from this research is the idea of space-time as a dynamic entity, rather than a fixed and unchanging backdrop for cosmic events. This shift in perspective suggests that at the quantum level, space-time may not be smooth or continuous as previously thought. Instead, it appears to possess a granular structure akin to a fabric woven from discrete units. This revolutionary concept challenges the long-held belief that the boundaries of the universe are fixed and immutable. Rather than being rigid walls, these boundaries may emerge from complex quantum processes, dramatically altering our perceptions of cosmic limits. Furthermore, emerging theories such as string theory and loop quantum gravity propose that the very fabric of the universe is interwoven through a web of quantum states. These theories suggest that what we perceive as the edge of the universe might not be a definitive boundary at all. Instead, it could represent the intersection of quantum information and gravitational forces, creating an interplay of complexities that we are only beginning to comprehend. This raises fascinating questions about black holes, long thought to be the ultimate boundaries where the laws of physics cease to function. Rather than being static, unyielding borders, black holes may function in a far more intricate way. New research in quantum gravity is exploring how information could potentially escape these regions, opening the door to a more nuanced understanding of what lies beyond them. As our understanding of these phenomena deepens, we find ourselves at the precipice of a paradigm shift. The boundaries of the universe are no longer distant concepts relegated to theoretical speculation. They are active areas of research, dynamic zones where quantum mechanics and gravitational forces interlace. Each discovery brings us closer to unlocking the mysteries of space-time, leaving us with more questions than answers, but also propelling us toward a more complete understanding of the cosmos. The implications are profound, urging us to reconsider the very fabric of reality and our place within it. The discovery of extraterrestrial life could serve as a catalyst for a major transformation in how we view the universe, particularly with respect to its boundaries, both physical and metaphorical. Traditionally, the edge of the universe has been understood in terms of its observable limits, defined by the expanse of space and the distances we can measure. However, the confirmation of life beyond Earth would prompt a radical reevaluation not only of where the universe ends, but of the very notion of isolation. If life exists elsewhere, it would challenge the long-held assumption that Earth is the sole cradle of life, suggesting that the universe may be teeming with life in places previously considered inhospitable. Such a revelation would raise many questions about the distribution of life across the universe. How do galaxies and cosmic structures influence where life can take hold? How might different forms of life evolve under varying environmental conditions? The discovery of extraterrestrial civilizations could indicate that we are not alone in a static universe, but part of a dynamic, interconnected cosmic system, where life evolves under conditions we are only beginning to understand. This new perspective would likely spark inquiries into how life interacts with its environment, how planetary systems develop, and how galaxies influence the paths of life within their gravitational spheres. In this context, the edge of the universe would no longer be defined strictly by physical limitations, but as a vibrant frontier of discovery. It would challenge our assumptions about solitude in the cosmos, pushing us to reimagine the universe as a vast, interconnected expanse, rich with the potential for life and wonder. However, communicating with potential extraterrestrial civilizations would present its own set of monumental challenges, not the least of which is the sheer vastness of space itself. The observable universe stretches over 13.8 billion years in every direction. While we can detect light from distant stars and galaxies, much of the universe lies beyond our reach, hidden in the darkness of the unobservable. The immense distances involved present a formidable barrier. Even if we were able to send a signal, it might never reach another intelligent species. They could be separated from us by incomprehensible distances, or the signal might be lost in the fabric of space-time, making meaningful contact a formidable challenge. Time, too, presents an additional obstacle. The universe is not static, it is constantly expanding. This expansion means that galaxies are moving away from each other at speeds that can exceed the speed of light due to the stretching of space-time itself. By the time a message from Earth might reach another civilization, that civilization could have evolved, vanished, or moved so far beyond reach that communication becomes impossible. The expanding universe introduces a profound complication. Our efforts to reach out may be thwarted by the very nature of time and space itself, rendering the task of establishing contact with distant civilizations even more daunting. Ultimately, the quest to understand the boundaries of the universe invites us to confront the deepest mysteries of existence. It urges us to rethink the very nature of space and time, to question what constitutes the limits of the cosmos, and to consider the possibility that what we know today is only the beginning of a far greater journey, one that extends beyond the stars and into the very fabric of reality itself. The vast expanse of time, when considered in the context of interstellar communication, stretches the limits of our understanding. The journey that signals must take across the universe may span generations, perhaps even millennia, before we receive a response or our message is recognized by another civilization. This raises an uncomfortable truth. The time it takes for our signals to reach distant civilizations may be so long that they fade into the realms of forgotten history before ever yielding a meaningful reply. It's a daunting prospect, one that challenges our very sense of urgency and relevance in the cosmic timeline. However, this is not the only limitation we face. Technological constraints also profoundly influence our ability to reach out. Our current communication methods, like radio waves, face inevitable challenges. These signals, while useful, weaken over vast distances and can be disrupted by cosmic phenomena, such as dense gas clouds or the warping effects of gravitational waves. The farther our signals travel, the more likely they are to degrade or be lost entirely in the cosmic noise. And then there is the pressing question. What if other civilizations have developed entirely different technologies? What if they communicate using methods we have yet to even imagine? Their forms of communication could be so alien that our attempts to connect would either go unnoticed or be completely misinterpreted. Moreover, there is a deeper philosophical aspect to consider. Our understanding of intelligence in life is limited by our own human experiences. We can only speculate about how another intelligent species might think, perceive the universe, or even what they consider communication. The vast differences in languages, symbols, and cultural contexts could easily lead to profound misunderstandings. What we interpret as a signal or a gesture might be completely foreign to another species, making the prospect of meaningful communication all the more challenging. In this light, while the dream of contacting extraterrestrial civilizations is tantalizing, the many physical, technological, and conceptual barriers make it a complex, uncertain endeavor, one that is far from straightforward. At the same time, the discovery of exoplanets, planets orbiting stars outside our solar system, has revolutionized our understanding of the universe and our place within it. In the early 1990s, when scientists first detected these distant worlds, it opened up a new realm of possibilities, challenging everything we thought we knew about planetary systems. No longer confined to our own solar neighborhood, astronomers began to explore a staggering variety of planetary environments, sizes, and orbits. These discoveries revealed a stunning diversity of worlds, many unlike anything we had imagined. To date, over 5,000 exoplanets have been confirmed, and this number is steadily growing. Each of these discoveries pushes the boundaries of exploration, revealing worlds located light years away from our own. The methods we use to identify these planets, such as the transit and radial velocity techniques, are cutting edge and constantly evolving, allowing us to glimpse worlds beyond our wildest imaginations. Yet, even as our technology advances, the distances involved are so vast that our ability to study these exoplanets is still limited. Despite these challenges, scientists are now able to measure the atmospheres of some of these far-off worlds, looking for signs of life or conditions that could support it. This has profound implications for the field of astrobiology, sparking new questions about the potential for life elsewhere in the cosmos. In addition, the discovery of exoplanets has shattered many long-held assumptions about planetary formation and habitability. Some exoplanets orbit their stars at startlingly close distances, challenging the traditional concept of a habitable zone, the region around a star where conditions might be just right for life as we know it. These unexpected discoveries suggest that the universe may be far more hospitable than we once thought. The diverse conditions in which planets form, evolve, and exist have led scientists to reconsider the very nature of planetary systems and the factors that make a world suitable for life. Understanding exoplanets enriches our knowledge not only of celestial mechanics, but also of life's potential. Every new exoplanet discovered prompts us to question our own assumptions and to open our minds to the vast possibilities that exist in the cosmos. As researchers continue to analyze these distant worlds, the boundaries of our explorations seem to grow ever wider. Each new discovery leads to more questions about the nature of planets across different star systems, pushing us to rethink our concepts of life, technology, and the future of human exploration. The search for alien worlds is not merely about cataloging new planets. It is a pursuit that broadens our understanding of the universe and challenges us to consider how we might one day interact with life forms that could exist far beyond our home planet. With each exoplanet discovered, we are not simply adding to a list of cosmic coordinates. We are expanding the horizon of what we know about the universe itself, inviting us to wonder about the many forms of life that could exist across the stars. When we think about the search for life on distant planets, we are also contemplating our place in the universe. For centuries, Earth was thought to be a unique oasis of life in an otherwise barren cosmos. But as astronomers uncover more planets within the habitable zones of their stars, we are beginning to realize that life may not be a rare phenomenon confined to our tiny corner of the galaxy. Instead, it could be a common feature of the cosmos, one that exists in a multitude of forms and environments, each waiting to be discovered. The study of exoplanets provides new insights into the conditions necessary for life to thrive. Scientists examine factors such as the presence of water, the planet's atmosphere, and its distance from its host star to determine its potential for supporting life. This research opens up an entirely new frontier in our understanding of life's diversity across the universe. With thousands of exoplanets now confirmed, it becomes clear that our solar system is just one of countless cosmic neighborhoods, each one potentially harboring life in ways we have yet to imagine. Each new discovery brings us one step closer to understanding the vastness of the cosmos and the countless possibilities it holds for life. Moreover, this quest challenges us to rethink our very conception of life itself. Earth-based life, as we know it, thrives only under a delicate set of conditions. The precise balance of temperature, atmosphere, and chemical composition is what makes our planet uniquely hospitable. But what if life elsewhere doesn't follow the same rules? What if extraterrestrial life could flourish in environments completely different from our own, perhaps in ways we can barely imagine? This question stretches the boundaries of our understanding, urging us to rethink not only the nature of life, but the very principles of biology that govern it. The search for life beyond Earth pushes the limits of both our imagination and our scientific theories. It forces us to ask fundamental questions. What constitutes a living organism? Is it merely a biological process? Or could there be forms of life that defy our current definitions? In doing so, the search compels us to reshape our understanding of life on a cosmic scale. It suggests that the universe may be teeming with possibilities for life, worlds that until now we've overlooked or misunderstood. As we extend our reach further into the cosmos, the implications of discovering even the most primitive forms of life on another planet are profound. Such a discovery would transform our understanding of the universe. It would tell us that life is not some rare accident, but a fundamental aspect of the universe, woven into its very fabric. Life could be as common as stars, galaxies, and black holes, each one a potential cradle for countless forms of existence. This revelation would not just impact science. It would ripple through philosophy, culture, and our own conception of existence, urging humanity to reconsider its place in the grand scheme of things. The search for extraterrestrial life forces us to reassess not only the scale of the universe, but also our significance within it. The search for extraterrestrial intelligence, or SETI, plays a central role in this journey. For decades, SETI has been at the forefront of efforts to detect signals from beyond our solar system, reaching out into the vast unknown for any signs of intelligent life. Unlike traditional astronomy, which focuses on the observable universe, SETI shifts its focus toward the potential for advanced civilizations existing far beyond the stars we can see. The core of SETI's mission is to listen for signals, radio waves, and electromagnetic pulses that might emanate from alien civilizations. It is based on the premise that any sufficiently advanced civilization might use technologies similar to our own, generating detectable signals as a byproduct of their activities. To this end, SETI employs massive radio telescopes scanning the sky for unusual patterns in the radiation emitted by distant stars and galaxies. Interestingly, SETI does not limit itself to searching for obvious intentional signals. Much of their work involves analyzing signals that might initially be dismissed as mere noise. Over the years, the methods employed by SETI have evolved, incorporating advanced algorithms and machine learning to refine their search. As the universe continues to expand, so does the scope of SETI's work, constantly evolving to keep pace with new discoveries and technologies. What sets SETI apart is its collaborative approach. It's not just a singular pursuit, but a global endeavor. Initiatives like the Breakthrough Listen project have significantly broadened the scale of SETI's search, aiming to listen to 1 million stars in our galaxy alone and even beyond. This collaborative spirit fosters a vibrant scientific community, united by a shared sense of wonder and curiosity. Could we, as a species, be on the brink of discovering that we are not alone in the universe? Moreover, SETI's partnerships with universities, private organizations, and government agencies help push the boundaries of technological development. These collaborations lead to the creation of more sophisticated detection methods, enabling the team to probe even deeper into the cosmos. Yet, despite these advances, the philosophical questions posed by SETI remain daunting. What would it mean for humanity if we were to detect a signal from an intelligent civilization? How would it change our view of life itself and our place in the cosmos? There are significant challenges, of course. The vast distances between stars and the finite speed of light limit our ability to receive signals from civilizations that may exist billions of light years away. Even if advanced life exists, the chances of us detecting it are slim, yet the pursuit continues. It drives our curiosity, fuels our imagination, and compels us to explore the unknown in search of answers to some of humanity's oldest questions. As we venture further into the cosmos, we encounter even more profound mysteries, ones that not only defy our understanding of life, but challenge the very laws of physics. Take dark energy, for example. This elusive force makes up roughly 70% of the total energy density of the universe, yet we still have no idea what it actually is or how it works. It seems to be the driving force behind the accelerated expansion of the universe, but beyond that, it is a complete enigma. Understanding dark energy is crucial not just for the fate of the universe, but for our fundamental understanding of physics itself. Similarly, the cosmic microwave background radiation, the faint glow that remains from the Big Bang, holds vital clues to the early history of the universe. Yet, even this signature of the universe's birth holds secrets that we have yet to unlock. Scientists have noted inconsistencies in the temperature fluctuations of this radiation, discrepancies that suggest our understanding of the universe's expansion rate might be flawed. This phenomenon, often referred to as the Hubble tension, challenges current models of cosmology and hints that we may need to rewrite parts of the physics we thought we knew. The questions posed by these cosmic mysteries continue to beckon us forward. Each new discovery, each breakthrough, raises as many questions as it answers, leading us ever deeper into the unknown. And as we expand our search for life, for intelligence, and for understanding, we are forced to confront the most profound question of all: what is our place in the vast, expanding universe? Additionally, scientists are increasingly captivated by the elusive concept of cosmic inflation, a theory suggesting that just after the Big Bang, the universe expanded at an extraordinary rate. This rapid growth, according to the theory, occurred in a fraction of a second, setting the stage for the universe we know today. While the notion of cosmic inflation offers a compelling explanation for the uniformity and flatness observed throughout the cosmos, the intricacies of this process remain shrouded in mystery. Numerous questions continue to arise, especially surrounding the mechanisms that could have triggered such a dramatic expansion. What could have caused the universe to inflate at such a rapid pace, and what forces were at play in this sudden transition? These unanswered questions only add to the enigmatic nature of the cosmos, urging scientists to dive deeper into the fundamental forces shaping the universe's origins. As we venture further into the depths of the universe's beginnings, the idea of the universe's ultimate boundaries introduces another layer of complexity. Is there a definitive edge to the cosmos, or is it endlessly expanding, forever stretching into the unknown? If an edge does exist, what lies beyond it? These questions continue to challenge our understanding of cosmic limits. And as we probe these vast uncertainties, we are reminded that the universe, in all its grandeur, remains an uncharted expanse. It guards its deepest secrets, ever beckoning us to explore further and uncover what lies beyond the surface of our current knowledge. A crucial piece of evidence that helps us peer into the early stages of the universe is cosmic background radiation, often referred to as the afterglow of the Big Bang. This faint microwave radiation permeates the entire universe, offering a snapshot of its infant state. By analyzing the fluctuations in temperature and density within this radiation, scientists can piece together the story of the universe's first moments. However, anomalies within the cosmic background radiation are sparking a reevaluation of traditional theories about the universe's structure. One of the most perplexing anomalies is the alignment of temperature variations that appears defy the randomness one would expect in such a vast and chaotic system. In certain regions, the radiation displays patterns that cannot be easily explained by conventional models, leading scientists to hypothesize that these areas might be influenced by forces or structures beyond our current understanding. These mysterious patterns challenge one of the cornerstones of the widely accepted lambda cold dark matter (LCDM) model, which posits that the universe is homogeneous and isotropic at large scales. The anomalies suggest that perhaps the universe is not as uniform as once thought, pointing to the possibility of hidden structures or forces at play. Some cosmologists speculate that these irregularities might indicate the presence of remnants from other universes, or perhaps they represent cosmic features that we have yet to identify. Such revelations raise tantalizing questions. Could our universe be just one piece of a far grander multiverse? If this hypothesis holds, it would revolutionize our concept of boundaries, both within and beyond our observable universe, and challenge the limits of our scientific inquiry and imagination. These puzzling anomalies within the cosmic microwave background radiation demand more than just theoretical consideration. They push the boundaries of established models, compelling scientists to reconsider the fundamental principles of cosmology. The pursuit of answers leads to the exploration of new theories, which may ultimately reshape our understanding of the universe and its hidden mechanisms. The quest to unravel these mysteries transcends the data itself. It is a journey that expands the horizons of human curiosity and the endless pursuit of knowledge about the universe we call home. The discovery of colossal structures, such as the Great Wall and other superstructures in the cosmos, has opened new doors for understanding the overall architecture of the universe. Astronomers have uncovered vast formations that span immense distances, such as galactic walls, filaments, and clusters. These gigantic structures represent some of the largest organized entities ever observed, with superclusters like the Sloan Great Wall stretching across hundreds of millions of light years. Such colossal formations are not just awe-inspiring in their sheer scale, they also reveal crucial insights into the distribution of matter throughout the cosmos. These monumental structures indicate that the universe is not a homogeneous entity, but rather a complex web of regions where matter has congregated into massive clusters, creating walls, sheets, and filaments that are separated by vast voids. This non-uniform distribution of matter has profound implications for our understanding of cosmic evolution and the forces that govern the universe's structure. It suggests a delicate balance between opposing forces: gravity, which pulls matter together, and dark energy, which propels the expansion of the universe. The interplay between these forces shapes the formation of these superstructures, influencing the evolution of galaxies and their interactions over time. Exploring the limits of these vast structures takes us beyond the edge of our current observational capabilities. The formations we can detect may only be a fraction of what lies beyond our view, hinting at the possibility of a far larger and more complex universe. The Great Wall and other superstructures are not just points on a cosmic map. They are vital pieces of the puzzle that help us understand the vast and intricate web of the universe's architecture. In addition to these massive structures, scientists are also studying cosmic voids, immense regions of space that are largely devoid of galaxies. These voids, surrounded by denser areas filled with galaxies and clusters, form the skeleton of the cosmic web. Understanding these voids is crucial for cosmologists as they provide valuable insights into the universe's overall structure and evolution. These empty regions are not just gaps in space, they hold critical clues about the forces shaping the cosmos. Cosmic voids are thought to play an essential role in theories surrounding the universe's edge and its potential boundaries. Their enormous size allows them to influence the motion of galaxies, altering how they cluster and interact with one another. These voids also provide a clearer view of the cosmic microwave background, allowing scientists to refine their models of cosmic expansion. By examining the way voids interact with the background radiation, researchers can better understand the forces at play in the evolution of the universe. This, in turn, offers critical insight into the future of the cosmos, whether it will continue to expand indefinitely or eventually collapse. The study of cosmic voids reveals the non-homogeneous nature of the universe. Their existence suggests that the universe is not uniformly filled with matter, but rather that regions of varying density exist, each with its own distinct characteristics. This uneven distribution is crucial for understanding whether the universe has a definitive edge or whether it extends far beyond our current observational limits. Finally, cosmic rays, high-energy particles originating from some of the most extreme environments in the universe, are providing researchers with a unique way to study distant cosmic phenomena. These particles, which are often produced by events such as supernovae or the activity around black holes, travel through space and can provide valuable information about the conditions in their places of origin. By analyzing the composition and energy of these particles, scientists can gain insights into the environments from which they came. This includes details about magnetic fields, radiation levels, and the presence of various elements, all of which help us understand the processes that govern the most energetic and violent events in the cosmos. Through the study of cosmic rays, we gain a glimpse into the distant past of the universe and explore some of the most fascinating cosmic phenomena that lie beyond our direct observation. Cosmic rays, often perceived as just high-energy particles streaking through the vast expanse of space, hold far more significance than their simple definition suggests. They are, in fact, extraordinary messengers from the distant corners of the universe, carrying with them crucial information that might illuminate some of the most profound mysteries of the cosmos. Among the greatest enigmas in modern astrophysics are dark matter and dark energy, two elusive substances that together make up approximately 95% of the universe. For years, scientists have speculated about the potential role cosmic rays might play in unlocking the secrets of these hidden components. High-energy cosmic rays, as they traverse the vast stretches of space, may interact with dark matter in ways that could produce detectable signals. These signals, when captured and studied, could provide invaluable clues about the nature of dark matter, an invisible substance that exerts gravitational effects on visible matter, but has so far eluded direct observation. Such interactions might also reveal how dark energy, a mysterious force driving the accelerated expansion of the universe, affects the cosmos on the grandest scales. If this theory holds true, cosmic rays could be the key to understanding what lies beyond the observable universe, offering a glimpse into realms that remain hidden from conventional detection methods. Far more than just particles speeding through space, cosmic rays are akin to time capsules, each carrying a snapshot of the universe's distant past. They act as messengers, carrying vital information from regions of the cosmos far beyond the reach of our telescopes. Through careful study of these high-energy particles, scientists can investigate cosmic environments and events that would otherwise remain beyond our grasp. As we decode these cosmic messages, layer by layer, we gain an ever deeper understanding of the intricate fabric that makes up the universe, uncovering secrets that might otherwise remain shrouded in darkness. One of the most spectacular phenomena that cosmic rays help us explore is the nature of quasars, some of the brightest and most energetic objects in the universe. Quasars, short for quasi-stellar objects, are formed around supermassive black holes located at the centers of galaxies. These black holes consume surrounding gas and dust, producing colossal amounts of energy in the process. The resulting radiation is so intense that quasars can outshine entire galaxies, emitting energy across the electromagnetic spectrum from radio waves to X-rays. Due to their immense luminosity, quasars serve as cosmic beacons, allowing astronomers to probe the farthest reaches of the universe and peer back in time. One of the primary mysteries that quasars help to unravel is the nature of the early universe. By observing these distant objects, scientists can essentially look backward in time, sometimes billions of years, to an era when the universe was still in its infancy. Some quasars that we observe today formed when the universe was less than 1 billion years old. Their existence provides crucial information about the conditions that existed during the universe's early stages, shedding light on how galaxies and their central black holes grew and evolved in this primordial period. The rapid growth of supermassive black holes in the early universe raises fascinating questions. How did these black holes accumulate such vast amounts of matter in such a short span of cosmic time? The presence of quasars provides some answers, indicating that these supermassive black holes grew quickly, possibly by feeding on large quantities of gas or merging with other black holes. The energy output of quasars, in turn, affects the galaxies they reside in. This interaction between a galaxy and its central black hole is profound. It can influence the rate of star formation and shape the overall evolution of the galaxy. By studying quasars, astronomers aim to understand the complex relationship between galaxies and the supermassive black holes at their cores, offering insights into the mechanisms that drive the formation and growth of galaxies over cosmic time. Moreover, the light emitted by distant quasars provides valuable clues about the chemical composition of the universe. As this light travels across vast distances, it interacts with gas clouds in its path, absorbing specific wavelengths. By analyzing these absorption lines, scientists can identify the elements present in these gas clouds, revealing important details about the chemical evolution of the universe. The study of quasars, then, not only helps us understand individual objects, but also contributes to our broader understanding of the cosmos and its evolution over time. As we look back through history, humanity's view of the universe has evolved dramatically. Early civilizations, such as the Greeks and Babylonians, envisioned the cosmos as a fixed domed structure with Earth at its center. This geocentric model, though not scientifically accurate, provided a sense of order and completeness. It was the foundation upon which later ideas would be built. The transition from a geocentric to a heliocentric model, spearheaded by figures like Nicolaus Copernicus in the 16th century, was a monumental shift in our understanding of the universe. Copernicus proposed that the sun, not the Earth, was at the center of the solar system, challenging long-standing beliefs and opening up new possibilities for exploring the cosmos. The invention of the telescope and the subsequent advancements made by astronomers like Galileo and Tycho Brahe provided a broader view of the universe. These early tools allowed us to look beyond our solar system, revealing the existence of distant stars, planets, and eventually entire galaxies. By the 20th century, the development of the Big Bang theory revolutionized our understanding of the universe. This theory posits that the universe began as an incomprehensibly hot and dense point, expanding and cooling over billions of years. The Big Bang model suggested that the universe was not a static, confined space, but an ever-expanding entity. This realization raised profound questions about the nature of the universe. Was it infinite, or did it have some kind of edge? Today, we continue to explore these questions, and thanks to advances in astronomy and astrophysics, our understanding of the universe continues to deepen. With tools like the Hubble Space Telescope and the upcoming James Webb Space Telescope, we are poised to peer even further into the cosmos, uncovering new wonders and mysteries. Through the study of cosmic rays, quasars, and other astronomical phenomena, we are slowly piecing together the story of the universe, its origins, its evolution, and the nature of the invisible forces that shape it. As we delve deeper into the cosmos, we come closer to understanding our place in the vast, ever-expanding expanse of space. Historical models of the cosmos, though far removed from modern scientific thought, continue to shape the way we approach the universe today. As we strive to understand the universe's edges, we find ourselves grappling with concepts such as cosmic inflation and dark energy, forces that propel the universe's ever-expanding boundaries and influence its ultimate structure. Through advancements in technology, particularly with telescopes and the study of cosmic microwave background radiation, our understanding of the universe continues to evolve. Each discovery, from the movement of distant galaxies to the detection of faint whispers from the beginning of time, enriches the tapestry of knowledge that bridges past observations with present-day inquiries. This ongoing interplay between ancient insights and modern exploration paints a picture of scientific progress as a journey that, far from being linear, unfolds through a combination of both breakthroughs and refinements of earlier models. The evolution of our understanding is a dynamic conversation between past thinkers and the technologies that have emerged to test their theories. The Copernican revolution stands as one of the most significant turning points in the history of science. Prior to this monumental shift, the geocentric model, the belief that Earth sat at the center of the universe, dominated both scientific thought and the broader cultural worldview. This model was long accepted, not only because it seemed to align with everyday experience, but also because it resonated with religious and philosophical ideas of humanity's central importance in the cosmos. In this view, Earth was the focal point of creation, and all celestial bodies, sun, stars, planets, moved in orbits around it. However, when Nicolaus Copernicus introduced the heliocentric model in the early 16th century, proposing that the sun, not the Earth, was the center of the universe, he upended centuries of accepted thought. Copernicus's idea was a radical departure from the norm, and it presented a more elegant solution to the problem of retrograde motion in planets and the shifting of the seasons. Rather than relying on complex and convoluted models involving epicycles, small circular orbits within larger orbits, his heliocentric model offered a simpler and more coherent explanation of planetary motion. This model not only transformed the way astronomers thought about the motion of celestial bodies, but also redefined our place in the grand cosmic order. The profound impact of this idea rippled out, influencing other thinkers such as Johannes Kepler and Galileo Galilei. Kepler's work on planetary motion, most famously his discovery that planets moved in elliptical orbits, further solidified the heliocentric model. His laws dismantled the idea that the universe was perfect and unchanging, offering instead a dynamic, evolving system. Galileo, on the other hand, took Copernicus's theories and gave them tangible evidence with his telescope. His observations of Jupiter's moons provided proof that not all heavenly bodies orbited the Earth, further challenging the geocentric view. But the Copernican revolution was not just a shift in astronomical theory. It also sparked a broader philosophical and existential reevaluation. If Earth was not at the center of the universe, what did that mean for humanity's significance? This question went beyond science and into the realm of philosophy, reshaping humanity's self-conception. The idea that Earth was not the focal point of the universe forced a reconsideration of humanity's role and purpose in the cosmos. No longer could humans claim a unique or privileged position in the grand scheme of things. This seismic shift in understanding also laid the foundation for the scientific revolution. The heliocentric model championed observation, reason, and empirical evidence. These principles would become the bedrock of modern scientific inquiry, replacing the reliance on ancient authority and theological interpretation. As a result, the Copernican revolution became not only a pivotal moment in astronomy, but also a turning point in the development of modern science. The heliocentric model did more than challenge outdated ideas. It laid the groundwork for a new way of thinking about the universe. It was no longer enough to accept the heavens as an immutable and mysterious realm. Rather, the universe became something to be observed, studied, and understood through reason and experimentation. This intellectual shift extended beyond astronomy and touched all aspects of science and culture, sparking an era of innovation that continues to this day. As we look back at the journey from the geocentric to the heliocentric model, we see it as a symbol of the broader evolution of human thought. The shift in our understanding of the cosmos was not just about getting the science right. It was about reimagining the very nature of reality itself. This transformation in thought set the stage for a new age of exploration and discovery, one that would expand the boundaries of human knowledge and change the way we see the universe forever. In many ways, the Copernican revolution was just the beginning. It ignited an insatiable curiosity about the universe that has led to ever more sophisticated tools and models, from the development of the telescope to the invention of space travel. Yet, the insights gleaned from the observations of ancient civilizations continue to reverberate today. Ancient societies, such as the Babylonians, Egyptians, and Greeks, were some of the first to look to the stars and try to make sense of the cosmos. Their observations were foundational, laying the groundwork for future generations of astronomers. These early civilizations tracked the movements of the sun, moon, and stars with great precision, creating calendars and navigation systems that are still relevant today. Their ability to chart the skies with such accuracy continues to influence modern technologies, from GPS systems to our understanding of stellar dynamics. Moreover, the geocentric model, though ultimately disproven, sparked intense debate and inquiry about the structure of the cosmos. This intellectual curiosity set the stage for the scientific breakthroughs that would follow. The eventual shift to the heliocentric model was not just a scientific revolution. It was the culmination of centuries of observations, questions, and experiments that spanned cultures and civilizations. Today, as we stand at the forefront of modern cosmology, we can trace our understanding of the universe back to these ancient foundations. The questions that early astronomers grappled with are still being explored, but with more powerful tools and more refined models. Yet, even as our understanding expands, we continue to be guided by the same curiosity and drive for knowledge that spurred our ancestors to look up at the stars and wonder what lay beyond. Ancient cultures often viewed the celestial phenomena not just through the lens of observation, but through spiritual and philosophical perspectives, weaving narratives that resonated deeply with the human experience. These stories remind us that humanity's quest for understanding the universe is intrinsically connected to our desire for meaning and purpose. As we delve into the astronomical observations of ancient civilizations, we discover not only the origins of our scientific journey, but also a reminder of our shared sense of awe and curiosity. These early observations continue to fuel modern cosmological theories, drawing a bridge between the ancient world and contemporary scientific thought. The insights of figures like Aristotle and Ptolemy, who were central to ancient scientific inquiry, laid the foundational concepts that would influence astronomical thinking for centuries. Aristotle, living in the 4th century BCE, made profound contributions to natural philosophy and physics. One of his most significant ideas was the geocentric model of the universe, which posited that Earth was the center of the cosmos, surrounded by 9 concentric celestial spheres. In his view, the heavenly bodies moved in perfect, unchanging circles, reflecting his belief in the ultimate perfection of the heavens. Aristotle's theories didn't only shape astronomy, they also impacted the realms of philosophy, biology, and physics, establishing a framework that dominated Western thought for nearly 2,000 years. Following Aristotle, the 2nd century astronomer Ptolemy advanced this geocentric model with greater precision in his monumental work, Almagest. Ptolemy introduced the concept of epicycles, explaining how planets moved in small circles, or epicycles, while orbiting Earth in larger circles. This ingenious modification helped explain the retrograde motion of planets, where they seemed to reverse direction in the sky. Ptolemy's model was so influential and accurate for its time that it went unchallenged until the revolutionary ideas of Nicolaus Copernicus in the 16th century. Despite being flawed by modern standards, Aristotle's and Ptolemy's conclusions were based on careful empirical observation, and their acceptance reflects the philosophical and cultural climate of their era. The acceptance of these ideas was a testament to the rigorous scholarly traditions of the time, which codified knowledge through detailed observations and writings. The geocentric view, with its combination of empirical inquiry and spiritual beliefs, had a lasting impact, shaping not only astronomy, but also influencing the broader intellectual traditions of the medieval period and the Renaissance. It provided a stable framework upon which future thinkers would build, although the paradigm would eventually be upended. It wasn't until Copernicus proposed the heliocentric model, suggesting that the sun, rather than Earth, was the center of the universe, that the deeply ingrained ideas of Aristotle and Ptolemy began to unravel. Understanding the roles these thinkers played offers a fascinating glimpse into the evolution of scientific thought, highlighting the gradual shift from philosophical reasoning to empirical observation in our understanding of the cosmos. In addition to philosophers and scientists, artists and illustrators have played a crucial role in helping us comprehend the vastness of the universe. The enormity of space often defies our mental capacity to fully grasp its scale, but artists bridge this gap by transforming abstract scientific concepts into visual representations that make them tangible. Through their work, they bring to life complex phenomena like supernovae, black holes, and even the cosmic microwave background radiation, helping to make science resonate on an emotional level. These artistic renderings do more than simply clarify scientific ideas. They evoke curiosity and wonder, compelling people to explore further. Artists infuse their cosmic depictions with humor, drama, or beauty, creating a visual language that appeals to both the mind and the heart. Their illustrations capture the imagination, drawing in people who may not typically engage with the scientific community or its literature. These visuals spark conversations and questions, such as, what lies beyond the edge of our night sky? This sense of wonder is the fuel that keeps the quest for knowledge alive, motivating both scientists and laypeople alike to look deeper into the mysteries of the universe, pushing the boundaries of our understanding ever further. Moreover, artists collaborate closely with scientists to ensure their representations of the cosmos are grounded in scientific accuracy while remaining visually captivating. These collaborations result in artwork that is not only informative, but also highly imaginative, providing a bridge between the known and the unknown. The process of transforming raw scientific data, such as the most recent observations from powerful space telescopes, into compelling visuals plays a critical role in communicating complex ideas about the universe that might otherwise be difficult to understand. This blending of art and science underscores the vital importance of visualization as an educational tool, allowing us to grasp concepts that would remain abstract without a visual counterpart. Artists and illustrators act as translators of the cosmos, turning the unfathomable mysteries of the universe into forms we can appreciate and comprehend. Their work doesn't just inform, it invites us to expand our perspectives, urging us to question our place in the vast expanse of the cosmos. It nurtures our inherent desire to explore the unknown, to look beyond our world and wonder about the limitless possibilities that exist just out of reach. This artistic endeavor is not only about beauty, but about sparking curiosity, igniting the human urge to venture deeper into the realms of science and discovery. Filmmakers, too, face unique challenges when it comes to depicting the universe's vastness. One of the most daunting hurdles they encounter is capturing the immense scale of space. The universe stretches across an inconceivable distance, with galaxies often separated by millions of light years. Translating this monumental scale into a visual narrative requires profound creativity and ingenuity. Often it means compressing time and space into manageable chunks, presenting the awe-inspiring grandeur of the cosmos while acknowledging the inherent limitations of human perception. The task becomes even more intricate when filmmakers attempt to convey the invisible dimensions and phenomena that shape the universe. Concepts such as dark matter and dark energy are essential to our understanding of the cosmos, yet they remain completely undetectable to the human eye. In this sense, filmmakers often rely on cutting-edge computer-generated imagery, CGI, and scientific visualization tools to represent these invisible elements. The challenge lies in keeping these artistic interpretations scientifically accurate while simultaneously engaging the audience's imagination. This delicate balance between educational integrity and visual excitement is a constant struggle, as filmmakers must meet the expectations of an audience that craves both entertainment and factual clarity. Misrepresentations can mislead viewers and distort essential scientific concepts, making it crucial for filmmakers to consult closely with scientists to ensure their depictions remain true to the latest research. However, the pursuit of cinematic flair can occasionally lead to oversimplifications or sensationalist portrayals that stretch beyond the boundaries of scientific reality. Additionally, time itself presents an incredibly complex factor in representing the universe. Not only does the universe stretch across vast distances, but it also unfolds over an incredibly long period. Events like the birth and death of stars or the formation of galaxies occur over spans of millions, even billions, of years. Translating this vast timeline into a compelling and relatable narrative for modern audiences can be a tricky task, especially since human lives are lived on a much shorter, more immediate scale. Filmmakers often adopt innovative storytelling techniques to make these events more digestible. They create narratives that anchor cosmic phenomena in terms that viewers can relate to, allowing audiences to grasp the profound nature of these events while tying them to familiar concepts. In this respect, visual metaphors play an essential role in helping the public understand the abstract ideas that underpin modern astrophysics. For example, when scientists explain the universe as a balloon inflating, they are offering a simple yet powerful visual to convey the expanding universe and the movement of galaxies. The image of an inflating balloon makes the concept of cosmic expansion more tangible, enabling the audience to visualize spatial relationships and dynamics that are otherwise beyond human comprehension. Such metaphors also provide a sense of emotional connection, transforming the universe from an abstract, impersonal concept into something relatable, even awe-inspiring. They make the unknown seem less alien, allowing individuals to see the universe not just as a cold expanse of space, but as a rich tapestry filled with possibilities. These metaphors also serve a crucial function in modern society, particularly in an era dominated by visuals and social media. Engaging imagery and easy-to-understand concepts can spark conversations and encourage collective exploration. The public can share these images and ideas, discussing the mysteries of the cosmos in accessible and inviting ways. By wrapping abstract theories in familiar, everyday visuals, these metaphors help bridge the gap between scientific thought and public understanding, igniting a passion for discovery and exploration. In addition to the work of artists and filmmakers, science museums and planetariums serve as key gateways to understanding the universe. These institutions create immersive, interactive environments that allow the public to engage with complex scientific concepts in a hands-on manner. Through exhibits that explore everything from the solar system to the observable universe, visitors are invited to dive into the mysteries of the cosmos. This approach encourages curiosity and a thirst for knowledge, making the science of the universe more accessible and digestible. Planetariums, in particular, play a vital role in bringing the universe to life. With their state-of-the-art projection systems, they can simulate the night sky that by transport viewers to distant galaxies and offer spectacular depictions of celestial events such as meteor showers or eclipses. These immersive experiences help demystify difficult ideas like the speed of light or the immense distances between stars by presenting them in ways that engage the imagination. By offering a visual representation of the universe, planetariums inspire wonder, fueling interest in further scientific exploration and study. Moreover, science museums and planetariums often host lectures, workshops, and educational programs that deepen public understanding of the universe's complexities. These programs bring together experts and enthusiasts, fostering a community dedicated to learning and scientific inquiry. By blending entertainment with education, these institutions nurture a culture of curiosity, encouraging visitors to ask questions, think critically, and expand their understanding of the cosmos. This fusion of education and exploration ensures that the fascination with space and science is not just a passive experience, but an active pursuit, one that continuously challenges our perceptions and sparks new discoveries. As centers of research and knowledge dissemination, science museums and planetariums have become essential hubs for inspiring future generations of scientists, engineers, and thinkers. By making the mysteries of the universe tangible, these spaces play a crucial role in bridging the gap between complex scientific concepts and the public. They not only foster scientific literacy, but also nurture a profound sense of responsibility towards our planet and the vast cosmos that surrounds us. In an era where science education is more vital than ever, science museums and planetariums stand as irreplaceable resources, offering unique opportunities to expand our understanding of the universe and our place within it. Meanwhile, music, often seen as an enigmatic form of expression, frequently serves as a gateway to experiencing the vastness of space. Composers have long drawn inspiration from celestial themes, using sound to evoke the awe and mystery inherent in the cosmos. The tonal shifts within a symphony, for example, can mirror the immense distances between galaxies or capture the eerie silence found in the void between stars. In this way, music becomes a journey that parallels the exploration of cosmic landscapes, creating a sensory bridge between the abstract and the emotional. The beauty of music lies in its ability to form the unfathomable concept of the universe into something tangible and deeply felt. Many contemporary composers intentionally weave elements of the natural world and astronomical concepts into their works. Imagine a composition designed to mimic the rhythmic pulse of a pulsar or the gentle undulations of a nebula forming. These musical pieces invite listeners to reflect on the grandeur of the universe while fostering a sense of connection to something far greater than themselves. The use of varying tempos and dynamics echoes the movement of celestial bodies, lending a physicality to the sounds that resonates with our own experiences of time and distance. Remarkably, some scientists have even analyzed the vibrations of celestial objects like black holes and translated them into music. These cosmic symphonies, both beautiful and haunting, deepen our understanding of the universe as they allow us to experience the scientific phenomena of space in ways we can hear and feel. This intersection between science and art highlights how the two realms can work together, enriching our comprehension of the cosmos. Music has become a medium through which complex astrophysical concepts are articulated and felt, offering new ways to experience the wonders of the universe. Ultimately, the interplay between music composition and the interpretations of the universe's vastness serves as a reminder that art and science are inherently intertwined. Music, in this sense, serves as a powerful reflection of our place in the cosmos, illustrating themes of isolation and interconnectedness. Through these compositions, we are led to ponder significant existential questions questions that draw parallels between our emotional journey and the infinite expanse of the universe. In the realm of speculative physics, the very notion of the universe's edges challenges our traditional understanding of cosmology. While many envision the universe as an endless and boundless entity, the possibility of actual edges provokes a deeper exploration of how we conceptualize the cosmos. One such fascinating theory is that of a toroidal or donut-shaped universe. In this model, space is curved in such a way that if one were to travel far enough in one direction, they would eventually return to their starting point. This theory challenges the conventional notion of edges and instead suggests a universe that loops back onto itself, an idea that flips our understanding of space and the boundaries of reality. As remarkable as it sounds, the toroidal universe presents an intriguing solution to the question of what lies beyond the observable universe. The answer in this case might be nothing at all. If the universe loops back on itself, every path would lead back to where it began, suggesting that the very concept of an edge becomes irrelevant. Other theories, like the idea of a multiverse, offer alternative perspectives. According to this view, our universe may simply be one among many, each with its own set of physical laws and dimensions. In this scenario, what we perceive as the edges of our universe may actually be the boundaries separating our realm from others. Some interpretations posit that these multiple universes exist within a vast higher dimensional space, where dimensions beyond the familiar three contribute to the very fabric of reality. Another idea emerges from the theory of cosmic inflation, which suggests that in the early stages of the universe's formation, it underwent rapid expansion. This expansion could have led to the creation of bubble universes, where some regions continue to expand while others remain compact. In this model, the edge of our universe may simply be the limit of our observable horizon, with much more lying beyond our current detection capabilities. These speculative theories invite us to reconsider the very nature of boundaries and edges in a universe that is in a constant state of flux, sparking curiosity about the fundamental structure of reality. The idea of time travel further captivates our imaginations, raising profound questions about the very nature of time and the universe. Traditionally, we perceive time as a one-way street, a linear progression from the past to the future. However, if time travel were possible, it would upend this conventional view, suggesting that time might not adhere to a fixed, unidirectional flow. Instead, it could open up a realm of possibilities where past, present, and future coexist in nonlinear ways. The implications of traveling back in time, for example, challenge the principle of causality, the idea that cause always precedes effect. If a time traveler were to alter a significant event in the past, they might inadvertently prevent their own existence, creating paradoxes that question the very nature of time itself. Such paradoxes, like the famous grandfather paradox, highlight that the timeline of events may not be as fixed as once believed. They suggest the existence of multiple realities or timelines, where altering the past could give rise to entirely new branches of the universe. In this sense, time travel expands our understanding of the universe, pushing beyond conventional boundaries and inviting us to explore the infinite possibilities of existence. Each of these speculative theories, from the shape of the universe to the possibility of time travel, pushes the limits of our imagination and challenges us to rethink our place in the cosmos. Moreover, various theories in physics, such as the multiverse theory, delve deep into the concept of infinite universes existing simultaneously. This perspective proposes that for every choice made, an entirely new universe branches off, creating a vast array of outcomes and possibilities. If time travel were ever to become a reality, it could allow individuals to journey through these alternate timelines, blurring the lines that have traditionally defined our universe. Time travel might not just offer a glimpse into parallel worlds, it could fundamentally alter the way we perceive reality itself. In this context, the implications of time travel remind us of something profound. Our understanding of the universe is far from fixed. It is constantly evolving. The intricate relationship between time and space could reveal that the universe is a far more complex, interconnected web than we currently imagine. As we continue to explore these concepts, we push the boundaries of both science and philosophy, opening new avenues for what it means to exist within this vast cosmic expanse. Thought experiments serve as powerful intellectual tools that allow scientists to stretch their imaginations and explore theoretical frameworks that might otherwise be out of reach. These exercises provide a platform for physicists to challenge established principles and concepts, all without the constraints of physical experimentation. In fields like cosmology and theoretical physics, where empirical data is often elusive, thought experiments offer a way to probe the deepest questions of existence. Instead of relying on tangible tools or direct observation, scientists lean on their imagination and reasoning to construct hypothetical scenarios, analyzing their potential outcomes. Take, for instance, Albert Einstein's thought experiments, which played a pivotal role in shaping his revolutionary theory of relativity. By mentally simulating the behavior of light in motion, Einstein was able to question traditional notions of space and time. Through this mental exercise, he discovered that the speed of light remains constant, no matter the observer's motion, and that time itself is relative. Its passage depends on how fast an observer is moving. Such groundbreaking insights, born from thought experiments, challenged and reshaped our understanding of the universe, revealing that our perceptions of reality may be far more fluid and elusive than we once thought. Moreover, these thought experiments are not merely academic curiosities. They provide us with a means to confront and wrestle with ideas that defy ordinary intuition. Consider the famous Schrödinger's cat scenario, a thought experiment that enters the bewildering realm of quantum mechanics. This scenario explores the strange concept of superposition, where particles can exist in multiple states simultaneously until observed. In Schrödinger's thought experiment, a cat in a sealed box can be simultaneously alive and dead, based on the behavior of a single subatomic particle. This paradox highlights the perplexing nature of quantum theory, inviting us to rethink fundamental assumptions about existence and reality. Thought experiments such as these serve as springboards for further scientific inquiry, challenging our understanding and provoking intense discussions on the most fundamental questions about the nature of life and the universe. In essence, thought experiments are indispensable in expanding the frontiers of human knowledge. They encourage scientists to think beyond the known and to formulate new theories that can later be tested through observation or experimentation. In a sense, they are a necessary precursor to tangible scientific breakthroughs. These exercises push us to reconsider our most basic assumptions, opening our minds to possibilities that lie far beyond what is immediately observable, and challenging the limits of human comprehension. As we venture further into these uncharted intellectual territories, thought experiments inspire new questions and fresh perspectives that help to redefine our place in the cosmos. One such radical rethinking of the universe comes in the form of the holographic principle, a concept that challenges our very understanding of reality. This idea suggests that the information contained within a three-dimensional volume of space could be encoded on a two-dimensional surface. In other words, the world as we experience it, a three-dimensional reality, might simply be a projection, much like a hologram, generated from information stored on a distant two-dimensional boundary. This principle emerged from the study of black holes. Traditionally, when matter falls into a black hole, it is thought to be lost forever, but researchers have found something astonishing. The information about that matter does not disappear. Instead, it is theorized to be imprinted on the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. This revelation forces us to reconsider not just the nature of black holes, but the very essence of reality itself. If the holographic principle holds, it could fundamentally alter our understanding of space, time, and matter. Rather than being separate, independent elements, these forces might merely be manifestations of deeper information encoded on the boundary of the universe. If this theory proves accurate, it could usher in a profound shift in our understanding of physics, potentially unifying diverse areas like quantum mechanics and gravity. The holographic principle presents an entirely new way of thinking about the cosmos, one that emphasizes interconnectedness and fluidity, rather than separation and rigidity. Just as a hologram creates a three-dimensional image from a two-dimensional surface, our three-dimensional reality might emerge from a deeper layer of information that exists beyond our sensory perceptions. This realization could have far-reaching implications, uniting disparate fields of study and leading to a more comprehensive and holistic understanding of how the universe functions and of our place within it. Explorations into hypothetical constructs such as Dyson spheres continue to challenge the limits of our imagination. First proposed by the theoretical physicist Freeman Dyson in the 1960s, the Dyson sphere is an ambitious idea, a structure capable of surrounding an entire star, harnessing its energy output for use by an advanced civilization. This concept pushes the boundaries of what we consider possible in terms of technological advancement and energy consumption, prompting us to think about the future of civilization in new and profound ways. A Dyson sphere would allow a society to capture the vast energy of a star, far surpassing any reliance on finite resources like fossil fuels. As we contemplate such futuristic constructs, we are forced to reconsider the limits of human potential and innovation. Could we one day reach the level of sophistication required to build such monumental structures? Dyson's idea suggests that once a civilization achieves a certain technological threshold, it would inevitably look to harness the power of entire stars, rather than depleting its local resources. This speculation invites us to reflect on our own technological trajectory, urging us to think more broadly about the future of energy, civilization, and our place in the universe. Moreover, the concept of Dyson spheres forces us to confront not only the limits of the observable universe, but also the profound possibility of extraterrestrial life. If advanced civilizations possess the ability to construct such immense structures, it compels us to ask difficult yet fascinating questions about the distribution of intelligent life across the cosmos. Are we truly alone in the universe? If these kinds of constructs are possible, and if civilizations can thrive to such an extraordinary extent that they can build Dyson spheres, then where are they? The search for these answers pushes the boundaries of our imagination, suggesting that the universe may be far more abundant and capable of sustaining life than we ever thought possible. The exploration of cutting-edge ideas like Dyson spheres does more than just spark curiosity. It broadens the horizons of our understanding of civilization, energy, and the very nature of existence. As we reflect on these possibilities, we are not merely fantasizing about the cosmos. We are forced to ponder our place in it, considering what our future might hold and how we might evolve as a species. Our exploration of the universe is also an exploration of ourselves, of our potential, and the untapped futures waiting to unfold. The concept of the universe's edge, long a source of intrigue for scientists and philosophers alike, continues to evolve as cosmological theories advance. For centuries, many have imagined the universe as a boundless expanse with a distinct and fixed boundary. However, recent breakthroughs in physics challenge this perception. What if the universe isn't just an infinite space, but an unbounded one, folding back on itself like the surface of a sphere? This idea suggests that if you were to travel far enough in one direction, you might eventually return to your starting point. This challenges the notion of a traditional edge, where everything simply ends. Even more thought-provoking are the implications of the multiverse theory, which posits that our universe is merely one of many, perhaps an infinite number, existing in parallel. If this is the case, the idea of a single, well-defined edge becomes almost irrelevant. Instead of thinking of our universe as a solitary entity with clear-cut borders, we are prompted to consider it as part of a far larger structure, woven into a much grander fabric of existence that might operate under entirely different laws of physics. This raises profound questions about the true nature of reality and our place in it, suggesting that we may be a small piece in a vast, interconnected cosmic puzzle. Moreover, with future advancements in technology, our methods of observation and exploration may unveil new phenomena that challenge everything we know. For example, anomalies in the cosmic microwave background radiation or unexplained gravitational effects could potentially reveal hidden dimensions or unknown layers of reality, previously beyond our reach. These revelations could suggest that the universe's edge is not just a physical limit, but a conceptual one, reshaping our understanding of space, time, and reality itself. As we venture deeper into these frontiers, it's likely that our understanding of the universe will continue to expand and evolve, constantly being reshaped by new discoveries and insights. The universe, we may find, is far more intricate, mysterious, and boundless than we ever imagined. Each new theory, each new breakthrough reminds us that we are only scratching the surface of a much greater mystery, one that holds within it the potential for revelations beyond our wildest dreams. At the heart of these explorations lies the question of the universe's boundaries. Is the universe finite or infinite? If it is finite, does it have a definitive edge, a boundary where space itself ends? This challenging notion forces us to reconsider everything we know about the fabric of space and time. Could the universe fold back upon itself, creating a loop that negates the idea of an edge? These are not just hypothetical queries, they are questions that stretch the limits of human understanding, challenging us to envision the universe in ways that go beyond our current scientific models. Another pressing question concerns the rate of expansion of the universe. Observations show that galaxies are not only receding from us, but doing so at an accelerating rate. This acceleration is attributed to a mysterious force known as dark energy, which is believed to drive this expansion. But what exactly is dark energy? Understanding this elusive force is crucial not only to our comprehension of the universe's present state, but also to its future. Dark energy is a key player in shaping the ultimate fate of the cosmos, and uncovering its true nature could profoundly alter our understanding of physics itself. In addition to these fundamental questions, there are also the challenges posed by the observable universe. Our ability to peer into the cosmos is limited by the finite speed of light and the universe's age, meaning that what we can see is only a small fraction of the entire cosmos. Beyond this observable limit, what lies hidden in the vast unknown? Are there regions of space teeming with matter that we simply cannot detect? Or could there be entirely separate universes, each governed by different laws of physics? These questions lie at the forefront of modern cosmology, constantly pushing us to expand our perceptions of reality and what might exist beyond the observable. Lastly, the structure of the universe itself presents further mysteries, particularly with regard to the cosmic microwave background radiation, the faint afterglow of the Big Bang. Scientists have noted slight irregularities in this radiation, leading them to wonder what these anomalies can tell us about the early universe. Could they provide clues to the nature of cosmic inflation, the rapid expansion that occurred just moments after the Big Bang? Understanding these irregularities could help us better comprehend how the universe evolved from a singular, compact point to the vast expanse we see today. As we continue to explore the cosmos, the questions grow ever more complex and fascinating, expanding the horizons of human knowledge. With each discovery, we inch closer to uncovering the true nature of the universe and, perhaps, our own place within it. The mysteries of the universe are far from resolved, and the quest for understanding is only just beginning. As scientists endeavor to unravel some of the most profound questions about the universe, every new discovery adds yet another layer to the intrigue, deepening our understanding of the cosmos. These revelations fuel our curiosity, pushing the boundaries of knowledge and continuously expanding our grasp of the enigmatic nature of the universe. In particular, the next generation of telescopes promises to unlock mysteries at the farthest reaches of space, pushing our vision of the universe's edge further than ever before. Astronomers and cosmologists have long been captivated by the vast unknown beyond our galaxy, but with advancements in technology and innovative design, these new instruments will be able to observe celestial objects and phenomena that were once out of reach. Equipped with cutting-edge tools, these telescopes will not only peer deeper into the cosmos, but will also provide clearer and more detailed images of distant galaxies, quasars, and other cosmic entities that have previously been obscured by distance or the limits of our observational capacity. One of the groundbreaking features of these advanced telescopes is their ability to capture images across multiple wavelengths of light, including infrared and ultraviolet. While visible light offers us a glimpse into the universe, it is the other wavelengths of light that reveal the hidden stories of the cosmos. For instance, many of the earliest galaxies, formed in the aftermath of the Big Bang, are detectable only in infrared light, emerging from the cosmic fog that once shrouded them. By focusing on these wavelengths, scientists are granted the opportunity to study the formation and evolution of galaxies, gaining a clearer understanding of how the universe expanded and evolved over billions of years. The upcoming James Webb Space Telescope, in particular, is designed with the express purpose of observing the universe's edge. This means that it will look at regions of space that contain light from stars and galaxies formed not long after the Big Bang itself. By studying this ancient light, astronomers hope to uncover invaluable insights into the early universe, potentially shedding light on some of the greatest mysteries of modern astrophysics, such as the nature of dark matter and dark energy. These elusive phenomena, which remain largely undetected and poorly understood, are at the forefront of scientific inquiry. As these new telescopes come online, they will not only deepen our understanding of the history of the universe, but they will also help refine our models of cosmic expansion. By observing distant galaxies and their behavior, these instruments will improve our comprehension of how the universe has expanded over time. The discoveries made through these advanced technologies could fundamentally alter our understanding of the cosmos, opening doors to new theories and models of how the universe operates. With every breakthrough, our perception of the cosmos shifts, revealing more about its structure and fundamental laws. The quest to understand the universe and the nature of its elusive boundaries is not just confined to observational astronomy. It is driving exploration in several other fields of study, each pushing the boundaries of human knowledge. A particularly exciting area of research lies in the realm of theoretical physics, where scientists are working tirelessly to reconcile the seemingly incompatible principles of quantum mechanics and general relativity. This groundbreaking integration, known as quantum gravity, could offer new insights into the behavior of black holes, the nature of space-time, and even the very fabric of the universe itself. In doing so, it could allow us to explore new realms beyond the observable universe, pushing the limits of what is known. Equally captivating is the study of dark matter and dark energy, two mysterious and invisible components that make up nearly 95% of the universe. Despite their overwhelming presence, dark matter and dark energy remain undetectable by traditional methods. However, new experiments, such as the search for weakly interacting massive particles, WIMPs, and investigations into the effects of dark energy are offering new avenues for discovery. Any breakthroughs in these areas could offer unprecedented clarity on the expansion of the universe, potentially revolutionizing our understanding of its structure and ultimate fate. Astrobiology, too, continues to capture the imagination of scientists as it explores the possibility of life beyond Earth. As missions venture into the farthest reaches of our solar system and beyond, researchers are discovering environments once thought inhospitable, which may in fact harbor life. The search for microbial life on Mars, the study of icy moons like Europa, and the exploration of exoplanets' inhabitable zones all hold the promise of revealing whether life exists elsewhere in the cosmos. These efforts have the potential to answer one of humanity's oldest questions: are we alone in the universe? In addition to these theoretical and observational breakthroughs, technological advancements in space exploration are playing a crucial role in expanding our ability to observe and understand the universe. The next generation of observatories, designed to detect phenomena such as gravitational waves, will allow scientists to study the cosmos in ways previously unimaginable. These instruments are expected to unlock new dimensions of space-time and provide insights into the universe's most perplexing events, from the collision of black holes to the formation of galaxies. As these discoveries unfold, they may challenge our current understanding and force us to reconsider the fundamental principles governing the cosmos. The discoveries made by these telescopes and instruments will likely lead to paradigm shifts in how we view the universe and our place within it. As researchers continue to unveil new cosmic phenomena, they will not only deepen our understanding of the universe's origins and evolution, but will also open new pathways for exploration and innovation. The quest for knowledge at the frontiers of space is far from over. Public interest in space exploration and the pursuit of scientific discovery also plays a vital role in shaping the course of research. When communities are captivated by the prospect of understanding the cosmos, they drive funding, attract talent, and influence the direction of scientific projects. The excitement generated by iconic missions such as the moon landings and Mars rover explorations has inspired entire generations of scientists, engineers, and enthusiasts. These successes have proven that human curiosity and determination can push the boundaries of what is possible, and in turn, they have led to increased investment in space missions and research. Societal interest in space exploration doesn't just propel funding, it also shapes the priorities of scientific research, as concerns about climate change, resource management, and the sustainability of life on Earth gain prominence. Space exploration has become an essential tool for addressing these global challenges. Technologies developed for space missions are often adapted for use on Earth, whether in the form of advanced communication systems, environmental monitoring, or renewable energy technologies. In this way, space research and exploration are intrinsically linked to our ability to solve pressing problems here at home. As public enthusiasm for exploration grows, so too does the drive for governments to allocate resources toward ambitious missions. The successful missions of the past have created a feedback loop, where public fascination with space exploration fuels continued investment and research. This synergy between scientific inquiry and societal interest is crucial for pushing the boundaries of human knowledge and ensuring that the pursuit of discovery continues to benefit all of humanity. As we look to the future, the next generation of telescopes and observational instruments will not only enhance our understanding of the universe, but will also reshape our relationship with the cosmos. They hold the potential to reveal answers to some of the most profound questions ever asked, challenging our perception of reality and expanding our place within the vast expanse of space. The journey to the frontier of the universe is just beginning, and with every new discovery, we take one step closer to unlocking the ultimate mysteries of existence.